Terraforming is the process of transforming a hostile environment on another planet into one that can support human life. It involves altering the atmospheric, climatic, and surface conditions to create a habitable environment. The concept, while ambitious, is rooted in scientific possibility and extensive research. By modifying a planet's atmosphere, we can potentially create conditions similar to those on Earth. This would include increasing oxygen levels, reducing harmful gases, and regulating temperatures. The goal is to create an environment where humans, animals, and plants can thrive. One of the primary objectives of terraforming is to create a stable climate. This involves controlling weather patterns, managing temperatures, and ensuring a balance between day and night cycles. Achieving a stable climate is crucial for sustaining life over long periods. Surface modification is another critical aspect of terraforming. This includes altering the soil composition to support agriculture, creating bodies of water, and building infrastructure. These changes are essential for developing a sustainable ecosystem. Terraforming also involves the introduction of microorganisms. These tiny life forms can help alter the planet's atmosphere and soil, making it more suitable for larger life forms. They play a crucial role in the early stages of terraforming by initiating biological processes. Advanced technology is essential for successful terraforming. This includes the use of robotics, artificial intelligence, and advanced materials. These tools enable us to perform large-scale modifications and monitor progress effectively. Terraforming is not just about creating a habitable environment, it's also about maintaining it. This requires ongoing efforts to manage resources, monitor ecological balance, and address any emerging issues. Sustainable management is key to long-term success. The potential benefits of terraforming are immense. It could provide new habitats for humanity, reduce overpopulation on Earth, and open up opportunities for scientific research. Additionally, it could lead to significant technological advancements. Ethical considerations are an important part of the terraforming debate. We must consider the potential impact on any existing ecosystems, the moral implications of altering another planet, and the long-term consequences for humanity. Balancing these concerns with the desire to explore and inhabit new worlds is a complex challenge. Legal issues also arise in the context of terraforming. Questions about ownership, rights, and responsibilities need to be addressed. International cooperation and legal frameworks will be essential to manage these aspects effectively. Public perception and support are crucial for the success of terraforming projects. Raising awareness, engaging with communities, and addressing concerns transparently can help build the necessary backing. Public involvement can drive innovation and ensure that projects align with societal values. Financial investment is another critical factor. Terraforming is an expensive and long-term endeavor, requiring significant funding from both public and private sectors. Strategic partnerships and funding mechanisms will be vital to sustain progress. Climate change on Earth provides valuable lessons for terraforming. Understanding how our actions impact the environment here can guide us in making responsible choices on other planets. This knowledge helps us develop effective strategies for creating and maintaining habitable conditions. Terraforming efforts can also drive advancements in renewable energy. Developing sustainable energy sources is essential for supporting life on another planet. Innovations in this area can benefit both Earth and our future off-world habitats. Education and research play a foundational role in terraforming. Encouraging scientific exploration, investing in research programs, and fostering a culture of innovation are essential. Educating the next generation of scientists, engineers, and explorers ensures continued progress and discovery in this ambitious field. Terraforming holds significant importance for the future of humanity. It offers the potential to expand our living spaces beyond Earth, providing new habitats for a growing population. As Earth's resources become strained, finding alternative locations for human settlement becomes crucial. Exploring and terraforming other planets can drive technological advancements. The challenges of creating habitable environments will push innovation in fields such as robotics, materials science, and environmental engineering. These breakthroughs can have far-reaching applications, benefiting life on Earth as well. The process of terraforming can enhance our understanding of planetary science. By studying other planets in detail, we gain insights into their geology, atmosphere, and potential for life. This knowledge can deepen our comprehension of Earth's own processes and history. Terraforming has the potential to ensure the long-term survival of humanity. In the event of catastrophic events on Earth, having habitable alternatives can serve as a form of planetary insurance. It provides a backup plan to preserve human civilization and biodiversity. Creating new ecosystems on other planets can help address the loss of biodiversity on Earth. By transferring species to new habitats, we can ensure their survival and promote ecological diversity. This can be particularly valuable for endangered species facing extinction. Terraforming can stimulate economic growth and create new industries. The need for specialized technology, materials, and expertise will open up job opportunities and drive economic development. Space exploration and colonization can become significant sectors of the global economy. The pursuit of terraforming can inspire and unite humanity. The shared goal of expanding our presence in the cosmos can foster international cooperation and collaboration. It encourages a sense of global unity and a collective effort towards a common purpose. Engaging in terraforming projects can enhance our problem-solving capabilities. The complex challenges involved require innovative thinking, interdisciplinary collaboration, and creative solutions. These skills can be applied to address various issues on Earth as well. Terraforming efforts can contribute to scientific discoveries and advancements. The research and experiments conducted during these projects can lead to breakthroughs in fields such as biology, chemistry, and physics. These discoveries can expand our knowledge and open new frontiers of science. The environmental management practices developed for terraforming can be applied to Earth. Techniques for climate control, resource management, and ecosystem restoration can be used to address environmental challenges on our own planet. This can help mitigate the impacts of climate change and promote sustainability. Terraforming can also promote a culture of exploration and curiosity. The desire to explore new worlds and push the boundaries of human capability can inspire future generations. It fosters a sense of adventure and a drive to seek out new knowledge and experiences. The potential for terraforming other planets can reshape our understanding of life in the universe. By creating habitable environments, we may uncover new forms of life, or understand the conditions necessary for life to thrive. This can expand our perspective on the diversity of life in the cosmos. The pursuit of terraforming can lead to the development of advanced life support systems. These systems are essential for sustaining human life in harsh environments and can be adapted for use on Earth. They can improve our ability to live in extreme conditions and enhance our resilience. Engaging in terraforming projects can stimulate global interest and investment in space exploration. The ambition to transform other planets can capture the public's imagination and drive funding and support for space missions. This increased interest can accelerate progress in space exploration and related technologies. Terraforming represents a bold step towards becoming an interplanetary species. It challenges us to think beyond our current limitations and envision a future where humanity thrives on multiple planets. This vision can inspire hope and a sense of limitless possibilities for the future of humankind. Venus and Mars, our neighboring planets, present unique challenges and opportunities for terraforming. Understanding their characteristics is crucial for any terraforming efforts. Let's delve into what makes these planets both fascinating and formidable. Venus, often called Earth's twin, is similar in size and composition to our planet. However, its atmosphere is incredibly dense, primarily composed of carbon dioxide, with clouds of sulfuric acid. This creates a runaway greenhouse effect, making surface temperatures soar to nearly 900 degrees Fahrenheit. The surface of Venus is rocky and volcanic, with vast plains, highland regions, and numerous volcanoes. Despite the harsh conditions, understanding Venus's geology can provide insights into Earth's geological past and future. The atmospheric pressure on Venus is about 92 times that of Earth, equivalent to the pressure found 3,000 feet underwater. This extreme pressure poses significant challenges for any potential human habitation or robotic exploration. Venus rotates very slowly, taking about 243 Earth days to complete one rotation. This slow rotation contributes to the planet's extreme surface temperatures and atmospheric dynamics. The combination of slow rotation and thick atmosphere creates unique weather patterns. Mars, on the other hand, is often considered the most viable candidate for terraforming. It has a thin atmosphere, composed mostly of carbon dioxide, with trace amounts of nitrogen and argon. The thin atmosphere means surface temperatures can be extremely cold, averaging around -80 degrees Fahrenheit. Mars has a diverse landscape, featuring the largest volcano in the solar system, Olympus Mons, and the deepest canyon, Valles Marineris. Its surface is covered with dust and rocks, with signs of ancient riverbeds and lakes, suggesting that liquid water once existed there. The atmosphere of Mars is too thin to support liquid water on its surface under current conditions. However, there are significant amounts of water ice at the polar caps and beneath the surface, which could be vital resources for terraforming. Mars has a day length very similar to Earth's, with a day lasting just over 24 hours. This similarity makes it easier to envision human settlers adapting to life on Mars. The planet also experiences seasons due to its axial tilt, though they are longer than Earth's seasons. The gravity on Mars is about 38% that of Earth's, which poses both challenges and advantages. Lower gravity could affect human health over long periods, but would also make construction and transport easier. Understanding how to adapt to this gravity will be key for long-term habitation. Mars lacks a global magnetic field, which means its surface is exposed to higher levels of cosmic radiation. This absence of a protective magnetic field requires the development of advanced shielding technologies to protect future settlers. Despite its challenges, Mars's potential for hosting life has intrigued scientists for decades. The discovery of recurring slope lineae, which may indicate seasonal liquid water flows, has fueled interest in the planet's habitability. Future missions aim to uncover more about its potential for supporting life. The thin atmosphere and lower gravity on Mars mean that any atmosphere introduced would need to be carefully managed to prevent it from being lost to space. Creating a stable atmosphere would involve generating greenhouse gases to warm the planet and thicken the atmosphere. Both Venus and Mars offer unique insights into planetary evolution and the potential for life. Studying these planets not only aids in terraforming efforts, but also enhances our understanding of Earth's place in the solar system. Each planet presents a distinct set of challenges that require innovative solutions and international collaboration. As we explore the possibilities of terraforming Venus and Mars, we embark on a journey of discovery and technological advancement. These efforts will push the boundaries of what is possible and pave the way for humanity's expansion into the cosmos. The future of terraforming holds immense promise and will shape the next era of space exploration. Terraforming Venus and Mars presents numerous challenges that require innovative solutions. The extreme conditions on both planets pose significant obstacles to creating habitable environments. One of the primary challenges is altering the atmospheric composition. On Venus, the thick carbon dioxide-rich atmosphere creates intense heat and pressure. Reducing these levels to create a livable climate is a monumental task. Mars, with its thin atmosphere, presents the opposite problem. Increasing the atmospheric density to retain heat and protect against radiation is crucial. This requires generating and maintaining a stable greenhouse gas layer. Temperature regulation is another significant challenge. Venus's surface temperatures are incredibly high due to its runaway greenhouse effect. Cooling the planet would involve massive geoengineering efforts. Conversely, Mars is extremely cold, with temperatures dropping to -80 degrees Fahrenheit. Warming the planet sufficiently to support liquid water and human life involves generating heat on a global scale. Radiation protection is vital, especially for Mars. Without a magnetic field, the surface is exposed to harmful cosmic rays. Developing effective shielding technologies is essential for long-term habitation. Creating a breathable atmosphere is a complex process. Both planets lack sufficient oxygen for human survival. Introducing and maintaining an oxygen-rich atmosphere involves extensive biological and chemical engineering. Water availability is a critical factor. Mars has polar ice caps and subsurface ice, but extracting and distributing this water presents logistical challenges. On Venus, the high temperatures make water management even more difficult. Soil fertility is another concern. The regolith on Mars lacks the nutrients necessary for plant growth. Developing methods to enrich the soil and support agriculture is vital for sustaining human colonies. Building infrastructure capable of withstanding harsh planetary conditions is imperative. Structures must endure extreme temperatures, atmospheric pressure, and potential seismic activity. Advanced materials and construction techniques are required. Energy generation and storage pose additional challenges. Reliable and sustainable energy sources are needed to power habitats, life support systems, and terraforming equipment. Renewable energy solutions must be adapted for each planet's unique environment. Logistics and supply chains must be established to support terraforming efforts. Transporting materials, equipment, and personnel from Earth to other planets involves complex planning and coordination. Ensuring a continuous and reliable supply chain is critical. The long timescales involved in terraforming present a unique challenge. Creating a habitable environment could take centuries. Sustaining long-term commitment and funding over such extended periods requires robust planning and international cooperation. Ethical considerations also play a significant role. The potential impacts on any existing microbial life must be carefully evaluated. Balancing the drive to terraform with the need to preserve native ecosystems is a delicate task. International collaboration is essential for successful terraforming. The scale of these projects requires the combined expertise and resources of multiple nations. Establishing and maintaining effective partnerships is key to overcoming the numerous challenges. Public perception and support can influence the progress of terraforming efforts. Engaging with communities, addressing concerns, and fostering a sense of shared purpose can help build the necessary backing. Public enthusiasm and involvement can drive innovation and sustain momentum. Terraforming Venus and Mars offers immense potential benefits for humanity. These endeavors could provide new living spaces as Earth's population continues to grow. Expanding our habitat into the solar system can alleviate pressure on our planet's resources. Advancing terraforming technology will drive innovation across multiple fields. The development of new materials, life support systems, and energy solutions can have wide-ranging applications. These technologies could improve life on Earth and support other space exploration missions. Creating new ecosystems on Mars and Venus can preserve Earth's biodiversity. Transferring species to new habitats ensures their survival, protecting them from extinction. This approach can help maintain ecological balance across multiple planets. The scientific knowledge gained from terraforming is invaluable. Understanding how to transform hostile environments deepens our grasp of planetary science. This knowledge can enhance our ability to address environmental challenges on Earth. Terraforming can stimulate economic growth by creating new industries. The demand for specialized technology, infrastructure, and transportation will drive economic development. Space colonization could become a major sector of the global economy. These projects foster international cooperation and unity. Working together on such ambitious goals encourages collaboration and shared purpose. This unity can strengthen global relations and drive collective progress. Terraforming efforts can inspire future generations to pursue careers in science and engineering. The vision of creating habitable worlds fosters a culture of exploration and curiosity. This inspiration can lead to significant educational and professional advancements. Exploring and inhabiting other planets ensures the long-term survival of humanity. In the face of potential global catastrophes, having alternative homes provides security. This diversification protects human civilization from extinction. The environmental management techniques developed for terraforming can be applied on Earth. Innovations in climate control, resource management, and sustainability can address our planet's challenges. These techniques promote a healthier, more sustainable Earth. Creating new opportunities for scientific research is another benefit. The unique environments of Venus and Mars offer unprecedented research possibilities. Studying these planets can lead to breakthroughs in various scientific fields. Terraforming can enhance our understanding of life's potential in the universe. Creating habitable conditions on other planets may reveal new forms of life. This discovery can expand our knowledge of biology and the conditions necessary for life. Engaging in terraforming projects can lead to significant advancements in renewable energy. Developing sustainable energy solutions for these planets benefits Earth as well. These advancements support global efforts to combat climate change. Public engagement in terraforming projects can drive societal progress. The excitement and ambition of these projects can unite communities and inspire collective action. This engagement fosters a sense of global citizenship and shared goals. The potential for terraforming to create self-sustaining colonies is transformative. These colonies can become independent, thriving societies. This expansion of human civilization into space marks a new era of exploration and growth. Lastly, terraforming represents the next step in human evolution. Expanding beyond Earth challenges us to reach new heights of innovation and adaptability. This evolution ensures that humanity continues to grow, thrive, and explore the vast universe. The idea of transforming other planets into habitable worlds has captivated human imagination for centuries. Early science fiction writers like H.G. Wells and Edgar Rice Burroughs introduced readers to the concept of altering alien environments to support human life. These imaginative stories laid the groundwork for future scientific exploration. In the mid-20th century, scientists began to seriously consider the feasibility of terraforming. Visionaries like Carl Sagan proposed early methods for transforming the atmospheres of Venus and Mars. Sagan's ideas included seeding the atmosphere with microorganisms to initiate ecological changes. One of the first scientific proposals for terraforming Mars was presented by Dandridge Cole in the 1960s. Cole suggested using nuclear explosions to heat the planet and release trapped carbon dioxide, creating a greenhouse effect. This bold idea highlighted the scale of intervention required to transform a planet. During the 1970s, NASA scientists explored the concept of terraforming Mars more thoroughly. They considered the potential of using mirrors in space to reflect sunlight onto the Martian surface, warming the planet. This approach aimed to initiate a runaway greenhouse effect, making the environment more hospitable. James Lovelock and Michael Allaby, in their 1984 book, The Greening of Mars, proposed using photosynthetic microorganisms to convert carbon dioxide into oxygen. Their vision included creating a self-sustaining ecosystem on Mars, similar to Earth's biosphere. The concept of using orbital mirrors to focus sunlight on Mars was revisited in the 1980s. Scientists speculated that large mirrors could significantly increase surface temperatures. This idea demonstrated the potential of using advanced technology to achieve terraforming goals. In the 1990s, Robert Zubrin's Case for Mars outlined a comprehensive plan for Martian colonization and terraforming. Zubrin proposed utilizing local resources, such as water ice and carbon dioxide, to support human settlements. His work inspired a new generation of scientists and engineers to pursue the dream of terraforming. Around the same time, NASA's Mars terraforming studies assessed the feasibility of various terraforming techniques. These studies included the use of greenhouse gases to warm the planet and the potential for microbial life to kickstart ecological processes. These assessments provided a scientific foundation for future terraforming efforts. In popular culture, films like Total Recall and Red Planet brought the concept of terraforming to a wider audience. These movies depicted dramatic and often fantastical visions of transforming Mars into a livable world. They fueled public interest and imagination regarding the possibilities of planetary engineering. The 21st century has seen renewed interest in terraforming, driven by advancements in technology and space exploration. Companies like SpaceX have articulated bold plans for colonizing Mars, including the long-term goal of terraforming. These modern efforts build on decades of scientific and imaginative groundwork. Researchers have also explored the potential for terraforming Venus, despite its harsh conditions. Ideas such as creating floating cities in the upper atmosphere or using solar shades to cool the planet have been proposed. These concepts highlight the diverse and creative approaches to making Venus more hospitable. The idea of using synthetic biology to aid terraforming has gained traction in recent years. Scientists are investigating how genetically engineered organisms could survive on Mars and initiate ecological changes. This approach combines biology and technology to tackle the challenges of planetary transformation. The growing interest in terraforming is also reflected in academic research. Universities and research institutions are studying the environmental, ethical, and technical aspects of transforming other planets. This interdisciplinary approach is crucial for addressing the complex challenges of terraforming. The development of space technology has made the prospect of terraforming more tangible. Advances in rocketry, robotics, and life support systems bring us closer to realizing these ambitious goals. Continued innovation is essential for making terraforming a reality. As we look to the future, the early concepts of terraforming serve as both inspiration and foundation. The pioneering ideas of scientists and visionaries have shaped our understanding of what is possible. Building on their work, we move closer to transforming the dream of habitable worlds into reality. Science fiction has profoundly influenced the concept of terraforming, inspiring both public imagination and scientific inquiry. Early writers like H.G. Wells and Olaf Stapledon depicted transformative planetary engineering in their novels, setting the stage for future explorations. In the mid-20th century, authors such as Ray Bradbury brought the idea of terraforming to a wider audience. His classic work, The Martian Chronicles, explored the colonization and transformation of Mars, blending human drama with planetary science. Isaac Asimov's Foundation series also touched on terraforming, envisioning advanced technologies that could reshape entire planets. His detailed and scientifically grounded approach made the concept more tangible for readers and scientists alike. Frank Herbert's Dune series provided a complex and richly detailed vision of terraforming. The planet Arrakis, with its harsh desert environment, is gradually transformed through the efforts of its inhabitants. Herbert's work highlighted the ecological and socio-political challenges of such endeavors. Kim Stanley Robinson's Mars trilogy is one of the most influential works on terraforming. His detailed and realistic portrayal of the colonization and transformation of Mars has inspired many in the scientific community. Robinson's work addresses the technical, ethical, and environmental aspects of terraforming. Arthur C. Clarke, in his novel The Sands of Mars, explored the practicalities of living on and transforming the Red Planet. Clarke's scientifically plausible scenarios have influenced both space enthusiasts and professionals in the field. Science fiction films have also played a crucial role in popularizing the concept of terraforming. The 1990 film Total Recall, based on Philip K. Dick's story, showcased dramatic terraforming technology that could transform Mars almost instantaneously. Ridley Scott's The Martian, adapted from Andy Weir's novel, presented a more grounded and realistic depiction of living and working on Mars. The film's success brought widespread attention to the challenges and possibilities of Mars colonization. Television series like The Expanse have further explored terraforming within the context of a richly developed solar system. The show's detailed world-building and attention to scientific plausibility have captivated audiences and sparked interest in planetary engineering. Video games such as Sid Meier's Alpha Centauri and Surviving Mars allow players to engage with the challenges of terraforming. These interactive experiences make the concept accessible and engaging, fostering a deeper understanding of the complexities involved. Science fiction has not only entertained but also educated the public about the potential of terraforming. By imagining diverse scenarios and solutions, these works have broadened our understanding of what might be possible. Many scientists and engineers working on space exploration today cite science fiction as a major influence. The genre has provided a creative foundation that stimulates innovative thinking and problem-solving in real-world applications. As humanity's interest in space exploration grows, science fiction continues to inspire new generations. The imaginative visions presented in literature, film, and games encourage us to push the boundaries of what is possible. Science fiction's influence extends beyond entertainment, shaping public policy and funding for space missions. The genre's ability to capture the imagination of policymakers and the public alike has been instrumental in advancing space exploration goals. The ongoing dialogue between science fiction and scientific reality ensures that the dream of terraforming remains vibrant and evolving. As we move closer to making these ideas a reality, the stories that inspired us will continue to play a crucial role in guiding our efforts. The initial scientific studies on terraforming began with examining the basic environmental conditions of Mars and Venus. Researchers aimed to understand the feasibility of altering these planets to support human life. Early studies focused on the composition of their atmospheres and surface conditions. Carl Sagan was one of the first scientists to propose concrete methods for terraforming. In the 1960s, he suggested using microorganisms to convert Venus's carbon dioxide into oxygen. This idea laid the groundwork for biological approaches to planetary engineering. In the 1970s, NASA began to seriously explore the concept of terraforming Mars. Their studies included examining the planet's climate, potential water sources, and the effects of its thin atmosphere. These early investigations were crucial for developing more detailed terraforming strategies. Researchers also looked into the possibility of using greenhouse gases to warm Mars. By releasing gases like carbon dioxide and methane, they hoped to create a runaway greenhouse effect. This approach aimed to raise the planet's temperature and increase atmospheric pressure. The Viking missions to Mars in the 1970s provided valuable data. These missions helped scientists understand the planet's surface and atmospheric conditions better. The information gathered was essential for refining terraforming theories and models. Studies in the 1980s explored the potential of using orbital mirrors to reflect sunlight onto Mars. These mirrors could significantly increase surface temperatures, aiding in the creation of a more hospitable climate. This idea highlighted the innovative technologies that could be employed in terraforming. Research also focused on the availability of water on Mars. Scientists examined the polar ice caps and the possibility of subsurface ice. Water is a critical resource for supporting human life and ecological systems, making these studies vital for terraforming plans. Venus posed a different set of challenges due to its extreme heat and atmospheric pressure. Initial studies considered ways to cool the planet, such as introducing reflective particles into the upper atmosphere. These particles could reduce the amount of sunlight reaching the surface. The concept of using large shades or mirrors to cool Venus was also explored. By blocking a portion of the sunlight, these structures could help lower surface temperatures. This approach demonstrated the need for large-scale engineering solutions. Studies on the potential biological aspects of terraforming also emerged. Researchers investigated how microorganisms could be used to alter planetary atmospheres and soils. These studies combined biology and planetary science in innovative ways. Advances in space technology in the 1990s and 2000s provided new opportunities for terraforming research. Robotic missions to Mars, such as the Pathfinder and Curiosity rovers, offered detailed insights into the planet's geology and climate. These missions were crucial for validating earlier theories. Researchers also began to consider the ethical implications of terraforming. Studies explored the potential impact on any existing microbial life and the broader environmental consequences. These discussions highlighted the need for responsible planetary stewardship. In the 21st century, the concept of terraforming gained more serious consideration. Studies focused on developing practical methods and technologies. These included the use of synthetic biology to create organisms tailored for planetary environments. International collaboration became increasingly important in terraforming research. Scientists from around the world pooled their expertise to tackle the complex challenges. This collaborative approach is essential for making significant progress. Initial scientific studies laid the foundation for the ambitious goals of terraforming. They provided the necessary data, theoretical models, and technological innovations. As research continues, these early studies remain a cornerstone of our efforts to transform other planets into habitable worlds. As our understanding of planetary science advanced, so did the ideas about terraforming. Early concepts were often theoretical, but over time they became more practical and detailed. This evolution reflects both technological progress and deeper scientific insights. In the 1980s, the idea of using large-scale engineering projects to terraform planets gained traction. Scientists proposed building massive mirrors or shades in space to manipulate planetary climates. These ideas were ambitious, highlighting the potential for human ingenuity in space. The discovery of water ice on Mars in the late 20th century was a game-changer. It provided a tangible resource that could be used for terraforming. Scientists began to develop more concrete plans for using this ice to create a more Earth-like environment. As we entered the 21st century, the focus shifted to sustainable and realistic approaches. Researchers started considering how to use Mars's natural resources more effectively. This included using in-situ resource utilization, or ESRU, to support human colonies and terraforming efforts. The potential of synthetic biology emerged as a significant development. By engineering organisms that could survive and thrive on Mars, we could potentially kickstart ecological processes. These organisms could help transform the atmosphere and soil, making the environment more hospitable. Advances in technology also played a crucial role. The development of more sophisticated robotics and AI allowed for more detailed exploration and experimentation. These technologies made it possible to test terraforming concepts on a smaller scale before attempting larger projects. Theoretical models became more refined as well. With better data from Mars missions, scientists could create more accurate simulations of how different terraforming strategies might play out. These models helped identify the most promising approaches and potential pitfalls. The ethical considerations of terraforming also evolved. Early discussions were often speculative, but as the possibility became more real, the ethical debates grew more serious. Questions about the rights of potential Martian life forms and the environmental impact of terraforming became central to the discourse. Public perception and interest in terraforming grew alongside these scientific advancements. Space exploration missions and the popularization of science through media helped raise awareness. This public interest is crucial for garnering the support needed for large-scale projects. International collaboration became more pronounced in the evolution of terraforming ideas. Countries around the world recognized the shared benefits and challenges of space exploration. Collaborative efforts led to a more global approach to the science and ethics of terraforming. The vision of Elon Musk and SpaceX brought renewed focus to Mars. Musk's ambitious plans for colonizing Mars include long-term goals of terraforming. His influence has sparked new interest and investment in the field, pushing the boundaries of what might be possible. Research into greenhouse gas production for warming Mars continued to evolve. Scientists explored various methods for releasing gases trapped in the Martian soil and ice. These efforts aim to create a self-sustaining greenhouse effect to support human life. Innovative ideas such as creating artificial magnetic fields were proposed to protect Mars from solar radiation. This technology could help retain an atmosphere and shield future inhabitants. It's a testament to the creative thinking inspired by the challenges of terraforming. Venus remained a more challenging target, but ideas for cooling its atmosphere and creating floating habitats persisted. The evolution of these ideas reflects a growing understanding of how to tackle Venus's unique problems. Advanced materials and energy solutions are key to these concepts. The ongoing evolution of terraforming ideas shows a dynamic interplay between imagination, science, and technology. As we learn more about our neighboring planets, our strategies for transforming them become more sophisticated and achievable. This journey of discovery continues to push the limits of our capabilities and our vision for the future. Current research in terraforming focuses on both Mars and Venus, leveraging the latest advancements in technology and science. These efforts aim to overcome the substantial challenges each planet presents, bringing us closer to the dream of making these worlds habitable. On Mars, the focus has shifted towards sustainable methods of warming the planet. Researchers are exploring ways to release carbon dioxide from the Martian soil and ice caps to thicken the atmosphere. This process could help create a stable, warmer climate suitable for liquid water. One promising area of research involves using artificial greenhouse gases. Scientists are testing compounds that could efficiently trap heat in the Martian atmosphere. These gases would help raise temperatures and increase atmospheric pressure, making the environment more Earth-like. NASA's Perseverance rover is conducting experiments crucial for future terraforming. It carries an instrument called MOXIE, which converts carbon dioxide from the Martian atmosphere into oxygen. This technology is a vital step towards producing breathable air on Mars. In the realm of synthetic biology, researchers are engineering microbes that could survive in Martian conditions. These organisms could play a key role in transforming the soil and atmosphere. They might produce oxygen, fix nitrogen, or even break down toxic chemicals. Advanced robotics and AI are enabling more detailed exploration and experimentation on Mars. Autonomous robots can conduct experiments, build infrastructure, and gather data. These capabilities are essential for testing terraforming techniques on a small scale. Energy production on Mars is another critical area of research. Scientists are developing solar panels and nuclear reactors that could provide reliable power for human settlements and terraforming operations. Efficient energy systems are crucial for sustaining life and technology on Mars. The European Space Agency is collaborating on projects to explore and utilize Martian resources. These efforts include studying water extraction from the subsurface and developing habitats that can support human life. International cooperation is enhancing our collective ability to terraform Mars. On Venus, researchers are investigating ways to cool the planet and reduce its atmospheric pressure. One proposed method involves deploying a fleet of solar shades to reflect sunlight away from the planet. This could gradually lower temperatures and make the environment more manageable. The concept of floating cities in the upper atmosphere of Venus is gaining traction. At altitudes where temperatures and pressures are more Earth-like, these habitats could serve as initial bases for further exploration and terraforming efforts. This approach circumvents the harsh conditions on the planet's surface. Scientists are also exploring the potential of using Venus's atmosphere to produce breathable air and other resources. By extracting carbon dioxide and using chemical processes to produce oxygen, we could create habitable zones in the upper atmosphere. These efforts are still in the early stages but show promise. The study of Venus's geology is providing insights into its volcanic activity and history. Understanding these processes is essential for assessing the planet's potential for future transformation. This research could inform strategies for managing Venus's extreme conditions. Technological advancements in space travel are making it easier to send missions to Mars and Venus. Reusable rockets, advanced propulsion systems, and improved life support technologies are reducing the costs and risks associated with these missions. These developments are crucial for sustained exploration and terraforming efforts. Public and private partnerships are driving significant progress in terraforming research. Companies like SpaceX and Blue Origin are working alongside governmental space agencies to develop the necessary technologies and infrastructure. This collaboration accelerates innovation and resource mobilization. Educational institutions and research organizations are playing a vital role in advancing terraforming science. Universities around the world are conducting experiments, running simulations, and training the next generation of scientists and engineers. This academic involvement is essential for the continued growth of the field. As current research and developments continue to advance, the dream of terraforming Mars and Venus moves closer to reality. Each discovery, experiment, and technological breakthrough brings us one step nearer to transforming these distant worlds into new homes for humanity. The journey is complex and challenging, but the progress made so far is promising and inspiring. Terraforming is the process of transforming a hostile environment on another planet into one that can support human life. It involves altering the atmospheric, climatic, and surface conditions to create a habitable environment. The concept, while ambitious, is rooted in scientific possibility and extensive research. By modifying a planet's atmosphere, we can potentially create conditions similar to those on Earth. This would include increasing oxygen levels, reducing harmful gases, and regulating temperatures. The goal is to create an environment where humans, animals, and plants can thrive. One of the primary objectives of terraforming is to create a stable climate. This involves controlling weather patterns, managing temperatures, and ensuring a balance between day and night cycles. Achieving a stable climate is crucial for sustaining life over long periods. Surface modification is another critical aspect of terraforming. This includes altering the soil composition to support agriculture, creating bodies of water, and building infrastructure. These changes are essential for developing a sustainable ecosystem. Terraforming also involves the introduction of microorganisms. These tiny life forms can help alter the planet's atmosphere and soil, making it more suitable for larger life forms. They play a crucial role in the early stages of terraforming by initiating biological processes. Advanced technology is essential for successful terraforming. This includes the use of robotics, artificial intelligence, and advanced materials. These tools enable us to perform large-scale modifications and monitor progress effectively. Terraforming is not just about creating a habitable environment, it's also about maintaining it. This requires ongoing efforts to manage resources, monitor ecological balance, and address any emerging issues. Sustainable management is key to long-term success. The potential benefits of terraforming are immense. It could provide new habitats for humanity, reduce overpopulation on Earth, and open up opportunities for scientific research. Additionally, it could lead to significant technological advancements. Ethical considerations are an important part of the terraforming debate. We must consider the potential impact on any existing ecosystems, the moral implications of altering another planet, and the long-term consequences for humanity. Balancing these concerns with the desire to explore and inhabit new worlds is a complex challenge. Legal issues also arise in the context of terraforming. Questions about ownership, rights, and responsibilities need to be addressed. International cooperation and legal frameworks will be essential to manage these aspects effectively. Public perception and support are crucial for the success of terraforming projects. Raising awareness, engaging with communities and addressing concerns transparently can help build the necessary backing. Public involvement can drive innovation and ensure that projects align with societal values. Financial investment is another critical factor. Terraforming is an expensive and long-term endeavor, requiring significant funding from both public and private sectors. Strategic partnerships and funding mechanisms will be vital to sustain progress. Climate change on Earth provides valuable lessons for terraforming. Understanding how our actions impact the environment here can guide us in making responsible choices on other planets. This knowledge helps us develop effective strategies for creating and maintaining habitable conditions. Terraforming efforts can also drive advancements in renewable energy. Developing sustainable energy sources is essential for supporting life on another planet. Innovations in this area can benefit both Earth and our future off-world habitats. Education and research play a foundational role in terraforming. Encouraging scientific exploration, investing in research programs, and fostering a culture of innovation are essential. Educating the next generation of scientists, engineers, and explorers ensures continued progress and discovery in this ambitious field. Terraforming holds significant importance for the future of humanity. It offers the potential to expand our living spaces beyond Earth, providing new habitats for a growing population. As Earth's resources become strained, finding alternative locations for human settlement becomes crucial. Exploring and terraforming other planets can drive technological advancements. The challenges of creating habitable environments will push innovation in fields such as robotics, materials science, and environmental engineering. These breakthroughs can have far-reaching applications, benefiting life on Earth as well. The process of terraforming can enhance our understanding of planetary science. By studying other planets in detail, we gain insights into their geology, atmosphere, and potential for life. This knowledge can deepen our comprehension of Earth's own processes and history. Terraforming has the potential to ensure the long-term survival of humanity. In the event of catastrophic events on Earth, having habitable alternatives can serve as a form of planetary insurance. It provides a backup plan to preserve human civilization and biodiversity. Creating new ecosystems on other planets can help address the loss of biodiversity on Earth. By transferring species to new habitats, we can ensure their survival and promote ecological diversity. This can be particularly valuable for endangered species facing extinction. Terraforming can stimulate economic growth and create new industries. The need for specialized technology, materials, and expertise will open up job opportunities and drive economic development. Space exploration and colonization can become significant sectors of the global economy. The pursuit of terraforming can inspire and unite humanity. The shared goal of expanding our presence in the cosmos can foster international cooperation and collaboration. It encourages a sense of global unity and a collective effort towards a common purpose. Engaging in terraforming projects can enhance our problem-solving capabilities. The complex challenges involved require innovative thinking, interdisciplinary collaboration, and creative solutions. These skills can be applied to address various issues on Earth as well. Terraforming efforts can contribute to scientific discoveries and advancements. The research and experiments conducted during these projects can lead to breakthroughs in fields such as biology, chemistry, and physics. These discoveries can expand our knowledge and open new frontiers of science. The environmental management practices developed for terraforming can be applied to Earth. Techniques for climate control, resource management, and ecosystem restoration can be used to address environmental challenges on our own planet. This can help mitigate the impacts of climate change and promote sustainability. Terraforming can also promote a culture of exploration and curiosity. The desire to explore new worlds and push the boundaries of human capability can inspire future generations. It fosters a sense of adventure and a drive to seek out new knowledge and experiences. The potential for terraforming other planets can reshape our understanding of life in the universe. By creating habitable environments, we may uncover new forms of life, or understand the conditions necessary for life to thrive. This can expand our perspective on the diversity of life in the cosmos. The pursuit of terraforming can lead to the development of advanced life support systems. These systems are essential for sustaining human life in harsh environments and can be adapted for use on Earth. They can improve our ability to live in extreme conditions and enhance our resilience. Engaging in terraforming projects can stimulate global interest and investment in space exploration. The ambition to transform other planets can capture the public's imagination and drive funding and support for space missions. This increased interest can accelerate progress in space exploration and related technologies. Terraforming represents a bold step towards becoming an interplanetary species. It challenges us to think beyond our current limitations and envision a future where humanity thrives on multiple planets. This vision can inspire hope and a sense of limitless possibilities for the future of humankind. Venus and Mars, our neighboring planets, present unique challenges and opportunities for terraforming. Understanding their characteristics is crucial for any terraforming efforts. Let's delve into what makes these planets both fascinating and formidable. Venus, often called Earth's twin, is similar in size and composition to our planet. However, its atmosphere is incredibly dense, primarily composed of carbon dioxide, with clouds of sulfuric acid. This creates a runaway greenhouse effect, making surface temperatures soar to nearly 900 degrees Fahrenheit. The surface of Venus is rocky and volcanic, with vast plains, highland regions, and numerous volcanoes. Despite the harsh conditions, understanding Venus's geology can provide insights into Earth's geological past and future. The atmospheric pressure on Venus is about 92 times that of Earth, equivalent to the pressure found 3,000 feet underwater. This extreme pressure poses significant challenges for any potential human habitation or robotic exploration. Venus rotates very slowly, taking about 243 Earth days to complete one rotation. This slow rotation contributes to the planet's extreme surface temperatures and atmospheric dynamics. The combination of slow rotation and thick atmosphere creates unique weather patterns. Mars, on the other hand, is often considered the most viable candidate for terraforming. It has a thin atmosphere, composed mostly of carbon dioxide, with trace amounts of nitrogen and argon. The thin atmosphere means surface temperatures can be extremely cold, averaging around -80 degrees Fahrenheit. Mars has a diverse landscape, featuring the largest volcano in the solar system, Olympus Mons, and the deepest canyon, Valles Marineris. Its surface is covered with dust and rocks, with signs of ancient riverbeds and lakes, suggesting that liquid water once existed there. The atmosphere of Mars is too thin to support liquid water on its surface under current conditions. However, there are significant amounts of water ice at the polar caps and beneath the surface, which could be vital resources for terraforming. Mars has a day length very similar to Earth's, with a day lasting just over 24 hours. This similarity makes it easier to envision human settlers adapting to life on Mars. The planet also experiences seasons due to its axial tilt, though they are longer than Earth's seasons. The gravity on Mars is about 38% that of Earth's, which poses both challenges and advantages. Lower gravity could affect human health over long periods, but would also make construction and transport easier. Understanding how to adapt to this gravity will be key for long-term habitation. Mars lacks a global magnetic field, which means its surface is exposed to higher levels of cosmic radiation. This absence of a protective magnetic field requires the development of advanced shielding technologies to protect future settlers. Despite its challenges, Mars's potential for hosting life has intrigued scientists for decades. The discovery of recurring slope lineae, which may indicate seasonal liquid water flows, has fueled interest in the planet's habitability. Future missions aim to uncover more about its potential for supporting life. The thin atmosphere and lower gravity on Mars mean that any atmosphere introduced would need to be carefully managed to prevent it from being lost to space. Creating a stable atmosphere would involve generating greenhouse gases to warm the planet and thicken the atmosphere. Both Venus and Mars offer unique insights into planetary evolution and the potential for life. Studying these planets not only aids in terraforming efforts, but also enhances our understanding of Earth's place in the solar system. Each planet presents a distinct set of challenges that require innovative solutions and international collaboration. As we explore the possibilities of terraforming Venus and Mars, we embark on a journey of discovery and technological advancement. These efforts will push the boundaries of what is possible and pave the way for humanity's expansion into the cosmos. The future of terraforming holds immense promise, and will shape the next era of space exploration. Terraforming Venus and Mars presents numerous challenges that require innovative solutions. The extreme conditions on both planets pose significant obstacles to creating habitable environments. One of the primary challenges is altering the atmospheric composition. On Venus, the thick carbon dioxide-rich atmosphere creates intense heat and pressure. Reducing these levels to create a livable climate is a monumental task. Mars, with its thin atmosphere, presents the opposite problem. Increasing the atmospheric density to retain heat and protect against radiation is crucial. This requires generating and maintaining a stable greenhouse gas layer. Temperature regulation is another significant challenge. Venus's surface temperatures are incredibly high due to its runaway greenhouse effect. Cooling the planet would involve massive geoengineering efforts. Conversely, Mars is extremely cold, with temperatures dropping to -80 degrees Fahrenheit. Warming the planet sufficiently to support liquid water and human life involves generating heat on a global scale. Radiation protection is vital, especially for Mars. Without a magnetic field, the surface is exposed to harmful cosmic rays. Developing effective shielding technologies is essential for long-term habitation. Creating a breathable atmosphere is a complex process. Both planets lack sufficient oxygen for human survival. Introducing and maintaining an oxygen-rich atmosphere involves extensive biological and chemical engineering. Water availability is a critical factor. Mars has polar ice caps and subsurface ice, but extracting and distributing this water presents logistical challenges. On Venus, the high temperatures make water management even more difficult. Soil fertility is another concern. The regolith on Mars lacks the nutrients necessary for plant growth. Developing methods to enrich the soil and support agriculture is vital for sustaining human colonies. Building infrastructure capable of withstanding harsh planetary conditions is imperative. Structures must endure extreme temperatures, atmospheric pressure, and potential seismic activity. Advanced materials and construction techniques are required. Energy generation and storage pose additional challenges. Reliable and sustainable energy sources are needed to power habitats, life support systems, and terraforming equipment. Renewable energy solutions must be adapted for each planet's unique environment. Logistics and supply chains must be established to support terraforming efforts. Transporting materials, equipment, and personnel from Earth to other planets involves complex planning and coordination. Ensuring a continuous and reliable supply chain is critical. The long timescales involved in terraforming present a unique challenge. Creating a habitable environment could take centuries. Sustaining long-term commitment and funding over such extended periods requires robust planning and international cooperation. Ethical considerations also play a significant role. The potential impacts on any existing microbial life must be carefully evaluated. Balancing the drive to terraform with the need to preserve native ecosystems is a delicate task. International collaboration is essential for successful terraforming. The scale of these projects requires the combined expertise and resources of multiple nations. Establishing and maintaining effective partnerships is key to overcoming the numerous challenges. Public perception and support can influence the progress of terraforming efforts. Engaging with communities, addressing concerns, and fostering a sense of shared purpose can help build the necessary backing. Public enthusiasm and involvement can drive innovation and sustain momentum. Terraforming Venus and Mars offers immense potential benefits for humanity. These endeavors could provide new living spaces as Earth's population continues to grow. Expanding our habitat into the solar system can alleviate pressure on our planet's resources. Advancing terraforming technology will drive innovation across multiple fields. The development of new materials, life support systems, and energy solutions can have wide-ranging applications. These technologies could improve life on Earth and support other space exploration missions. Creating new ecosystems on Mars and Venus can preserve Earth's biodiversity. Transferring species to new habitats ensures their survival, protecting them from extinction. This approach can help maintain ecological balance across multiple planets. The scientific knowledge gained from terraforming is invaluable. Understanding how to transform hostile environments deepens our grasp of planetary science. This knowledge can enhance our ability to address environmental challenges on Earth. Terraforming can stimulate economic growth by creating new industries. The demand for specialized technology, infrastructure, and transportation will drive economic development. Space colonization could become a major sector of the global economy. These projects foster international cooperation and unity. Working together on such ambitious goals encourages collaboration and shared purpose. This unity can strengthen global relations and drive collective progress. Terraforming efforts can inspire future generations to pursue careers in science and engineering. The vision of creating habitable worlds fosters a culture of exploration and curiosity. This inspiration can lead to significant educational and professional advancements. Exploring and inhabiting other planets ensures the long-term survival of humanity. In the face of potential global catastrophes, having alternative homes provides security. This diversification protects human civilization from extinction. The environmental management techniques developed for terraforming can be applied on Earth. Innovations in climate control, resource management, and sustainability can address our planet's challenges. These techniques promote a healthier, more sustainable Earth. Creating new opportunities for scientific research is another benefit. The unique environments of Venus and Mars offer unprecedented research possibilities. Studying these planets can lead to breakthroughs in various scientific fields. Terraforming can enhance our understanding of life's potential in the universe. Creating habitable conditions on other planets may reveal new forms of life. This discovery can expand our knowledge of biology and the conditions necessary for life. Engaging in terraforming projects can lead to significant advancements in renewable energy. Developing sustainable energy solutions for these planets benefits Earth as well. These advancements support global efforts to combat climate change. Public engagement in terraforming projects can drive societal progress. The excitement and ambition of these projects can unite communities and inspire collective action. This engagement fosters a sense of global citizenship and shared goals. The potential for terraforming to create self-sustaining colonies is transformative. These colonies can become independent, thriving societies. This expansion of human civilization into space marks a new era of exploration and growth. Lastly, terraforming represents the next step in human evolution. Expanding beyond Earth challenges us to reach new heights of innovation and adaptability. This evolution ensures that humanity continues to grow, thrive, and explore the vast universe. Venus, often referred to as Earth's twin, is similar in size and structure to our planet. Its diameter is about 12,104 kilometers, making it only slightly smaller than Earth. This similarity has long intrigued scientists studying planetary formation and evolution. The surface of Venus is incredibly hostile, with temperatures averaging around 900 degrees Fahrenheit. These extreme temperatures are due to a runaway greenhouse effect, where the thick carbon dioxide atmosphere traps heat. Venus's surface pressure is about 92 times greater than Earth's, equivalent to the pressure found 3,000 feet underwater. This immense pressure makes it difficult for current technology to explore the surface for extended periods. The planet's surface is covered with vast plains of solidified lava, indicating a history of widespread volcanic activity. This volcanic terrain includes extensive lava flows, volcanic mountains, and large caldera formations. One of the most notable volcanic features is Maxwell Montes, the highest mountain on Venus, rising about 11 kilometers above the surrounding plains. This massive peak is located in Ishtar Terra, one of the planet's highland regions. Venus has a relatively young surface, geologically speaking, with most of it estimated to be between 300 and 500 million years old. This young surface is the result of a planet-wide resurfacing event likely caused by volcanic activity. The planet's surface is marked by numerous impact craters, though fewer than on other rocky planets. The dense atmosphere burns up smaller meteoroids, allowing only larger objects to reach the surface and create craters. Tesserae, or highly deformed regions of the surface, are unique to Venus. These areas consist of intersecting ridges and valleys, suggesting intense tectonic activity. Tesserae are some of the oldest surfaces on the planet, providing clues about its geological history. The atmosphere of Venus is composed primarily of carbon dioxide, with clouds of sulfuric acid droplets. These thick clouds reflect sunlight, making Venus the brightest planet in the night sky, but also obscuring direct observation of the surface. Surface winds on Venus are relatively slow, moving at a few kilometers per hour. However, the upper atmosphere experiences superrotation, with winds reaching speeds of up to 360 kilometers per hour, circulating the planet every 4 to 5 Earth days. Venus lacks a significant magnetic field, which differs greatly from Earth. This absence contributes to the stripping away of lighter molecules in the upper atmosphere by solar wind, affecting the planet's atmospheric composition over time. The planet rotates very slowly and in the opposite direction to most planets in the solar system, including Earth. A day on Venus lasts about 243 Earth days, while its year is about 225 Earth days, making a day longer than a year. Venus's thick atmosphere leads to a phenomenon known as the Venusian ionosphere, where solar radiation ionizes atmospheric gases. This ionosphere plays a crucial role in the planet's interaction with solar wind and its space environment. The surface of Venus has extensive networks of rift valleys and large mountain ranges, indicating complex tectonic processes. These features suggest that Venus has experienced significant crustal deformation, though the exact mechanisms remain a topic of research. Exploring Venus provides insights into the dynamics of Earth-like planets and their atmospheres. Understanding Venus's extreme environment helps scientists learn more about atmospheric processes, climate change, and planetary evolution, offering valuable lessons for Earth and other planetary bodies. Venus's atmosphere is extremely thick and composed primarily of carbon dioxide, accounting for about 96.5% of the total. This dense layer creates a powerful greenhouse effect, trapping heat and leading to surface temperatures hot enough to melt lead. The second most abundant gas in Venus's atmosphere is nitrogen, making up about 3.5%. This is significantly lower than the nitrogen levels found on Earth, but it still plays a role in the planet's atmospheric dynamics. Sulfur dioxide is present in trace amounts, but it is crucial in forming Venus's thick cloud layers. These clouds are composed of sulfuric acid droplets, creating a highly reflective and opaque layer that obscures the surface from direct observation. The atmosphere contains trace amounts of other gases, including water vapor, carbon monoxide, argon, and neon. These trace gases contribute to the complex chemical interactions within the Venusian atmosphere. The sulfuric acid clouds on Venus are concentrated in the upper atmosphere, between 50 and 70 kilometers above the surface. These clouds reflect about 75% of the sunlight that reaches Venus, making the planet incredibly bright when viewed from Earth. Beneath the sulfuric acid clouds lies a layer of thick, hazy air, where temperatures can reach up to 900 degrees Fahrenheit. This lower atmosphere is a region of intense heat and pressure, with conditions that are challenging for any exploratory equipment. The atmospheric pressure at the surface of Venus is about 92 times greater than that of Earth's. This immense pressure, combined with high temperatures, creates an environment similar to being 3,000 feet underwater on Earth. Venus's atmosphere is in a state of superrotation, where the upper layers of the atmosphere rotate much faster than the planet itself. Winds in the upper atmosphere can reach speeds of up to 360 kilometers per hour, completing a full rotation around the planet in just 4 to 5 Earth days. The absence of a significant magnetic field on Venus means its atmosphere is directly exposed to the solar wind. This exposure causes the gradual stripping away of lighter atmospheric molecules, such as hydrogen and helium, by the solar wind. The ionosphere of Venus, located between 120 and 300 kilometers above the surface, is a region where solar radiation ionizes atmospheric gases. This ionization process affects the planet's interaction with the solar wind and contributes to the loss of atmospheric particles. Venus's atmosphere exhibits a phenomenon known as the greenhouse effect, but on a much more extreme scale than Earth's. The thick carbon dioxide layer traps infrared radiation, leading to the incredibly high surface temperatures observed today. Lightning has been detected in Venus's atmosphere, primarily within the sulfuric acid clouds. This lightning activity suggests dynamic weather patterns and electrical discharges, similar to thunderstorms on Earth. The atmospheric composition of Venus has evolved over time, likely due to volcanic outgassing and chemical reactions. Understanding these processes helps scientists learn about the planet's geological and climatic history. Future missions to Venus aim to study its atmosphere in greater detail, focusing on the chemical interactions, cloud dynamics, and weather patterns. These studies are essential for understanding Venus's extreme climate and its implications for planetary science. The thick and hostile atmosphere of Venus provides a stark contrast to Earth's more temperate conditions. Studying Venus's atmospheric composition and behavior offers valuable insights into the potential for climate extremes and atmospheric processes on other planets. Venus has an incredibly harsh climate, dominated by extreme temperatures and dense clouds. Surface temperatures average around 900 degrees Fahrenheit, making Venus the hottest planet in the solar system. The thick atmosphere on Venus creates a runaway greenhouse effect. This effect is caused by the high concentration of carbon dioxide, which traps heat and prevents it from escaping back into space. Venus's cloud cover is composed mainly of sulfuric acid, reflecting most of the sunlight and giving the planet its bright appearance. These clouds cover the entire planet, creating a uniform and highly reflective layer. Despite the thick cloud cover, very little sunlight reaches the surface. The surface of Venus is shrouded in perpetual twilight, with only dim light filtering through the dense clouds. The weather on Venus is characterized by strong winds, especially in the upper atmosphere. These winds can reach speeds of up to 360 kilometers per hour, circling the planet in just 4 to 5 Earth days. In the lower atmosphere, closer to the surface, winds are much slower. They move at just a few kilometers per hour, but due to the high density of the atmosphere, they exert significant force. Lightning has been observed within Venus's clouds, indicating active and dynamic weather patterns. These lightning storms are similar to thunderstorms on Earth, but occur in an atmosphere filled with sulfuric acid. The planet experiences little variation in temperature between day and night due to the thick atmosphere. This uniform temperature distribution means that both the day and night sides of Venus are equally scorching. Venus's rotation is extremely slow and retrograde, meaning it rotates in the opposite direction to most planets in the solar system. One day on Venus lasts about 243 Earth days, while its year is only 225 Earth days. The slow rotation of Venus contributes to its unusual climate dynamics. Despite the slow rotation, the super-rotating atmosphere means that weather patterns can move quickly around the planet. There is no liquid water on the surface of Venus due to the extreme temperatures and pressures. Any water present would immediately evaporate or dissociate into hydrogen and oxygen, with the hydrogen escaping into space. The thick clouds of sulfuric acid in the atmosphere are a result of volcanic outgassing. These clouds form at high altitudes and gradually descend, contributing to the planet's hostile environment. The high surface pressure on Venus, about 92 times that of Earth, compresses the atmosphere and contributes to the extreme heat. This pressure is equivalent to being deep underwater on Earth, making it a significant challenge for exploration. Venus's climate has likely remained stable for hundreds of millions of years. The lack of plate tectonics and the presence of a thick atmosphere suggest that its climate has not undergone significant changes in the recent geological past. Understanding the climate and weather patterns of Venus is crucial for comparative planetology. By studying Venus, scientists gain insights into atmospheric processes, climate change, and the potential for similar phenomena on other planets. This knowledge is essential for understanding the diversity of planetary environments in our solar system and beyond. Venus's surface conditions are incredibly extreme and harsh. The surface temperature averages around 900 degrees Fahrenheit, hot enough to melt lead. This intense heat is due to the runaway greenhouse effect caused by the thick carbon dioxide atmosphere. The atmospheric pressure at the surface of Venus is about 92 times greater than Earth's, equivalent to the pressure found 3,000 feet underwater. This immense pressure makes it challenging for current technology to operate on the surface for extended periods. Venus's surface is predominantly composed of volcanic plains. These plains are formed from solidified lava flows, indicating extensive volcanic activity in the planet's history. Volcanism has played a significant role in shaping the Venusian landscape. One of the most notable features on Venus is Maxwell Montes, the highest mountain on the planet. This massive peak rises about 11 kilometers above the surrounding plains and is located in Ishtar Terra, one of Venus's 2 major highland regions. The planet's surface is also marked by numerous impact craters. These craters are fewer in number compared to other rocky planets because the dense atmosphere burns up smaller meteoroids. The craters that do exist are often well preserved due to the lack of weathering. Tesserae are highly deformed regions of the surface unique to Venus. These areas consist of intersecting ridges and valleys, suggesting intense tectonic activity. Tesserae are some of the oldest surfaces on the planet, providing valuable clues about its geological history. Rift valleys and large mountain ranges are also present on Venus, indicating complex tectonic processes. These features suggest significant crustal deformation, although the exact mechanisms differ from those on Earth. The surface of Venus is covered with a thick layer of rock and dust, primarily composed of basalt. This composition is typical of volcanic regions, supporting the idea that volcanism has heavily influenced the planet's surface. Venus's surface lacks liquid water due to the extreme temperatures and pressures. Any water present would quickly evaporate or break down into hydrogen and oxygen, with the hydrogen escaping into space. The surface shows evidence of widespread lava flows and large shield volcanoes. These features indicate that Venus has experienced significant volcanic activity, which may still be ongoing. The volcanic plains are dotted with numerous smaller volcanoes and lava domes. Venus also has vast flat regions called planitia. These low-lying plains are believed to be areas where lava has flowed and solidified, creating large expanses of relatively smooth terrain. These plains cover much of the planet's surface. The surface is relatively young in geological terms, with most regions estimated to be between 300 and 500 million years old. This youthfulness suggests that Venus underwent a planet-wide resurfacing event, possibly due to volcanic activity. In some areas, the surface is fractured into large blocks, indicating tectonic stresses. These regions of fractured terrain provide insights into the planet's tectonic activity and the forces shaping its surface. Venus has coronae, large circular features that may result from upwellings of molten rock from the mantle. These features are unique to Venus and provide important information about the planet's internal processes. Exploring Venus's surface conditions helps scientists understand the planet's geological and climatic history. The extreme environment poses significant challenges, but studying Venus offers valuable insights into the dynamics of Earth-like planets and the potential for similar conditions elsewhere in the solar system. Venus holds several potential resources that could be valuable for future exploration and possible colonization. The most abundant resource on Venus is its thick atmosphere of carbon dioxide. This CO2 can be processed to produce oxygen for breathing and carbon for building materials. The sulfuric acid in Venus's clouds can be broken down into sulfur and water. Sulfur can be used in various industrial processes, while water is essential for sustaining human life. Extracting and purifying water from sulfuric acid is a complex but potentially rewarding challenge. Venus's surface contains a wealth of mineral resources. Basalt, which makes up much of the surface, contains useful elements like iron, magnesium, and aluminum. These minerals can be extracted and used for construction and manufacturing. The highlands of Venus, such as Ishtar Terra and Aphrodite Terra, may hold concentrations of precious metals. Gold, platinum, and other valuable metals could be mined, assuming technology can be developed to withstand the extreme surface conditions. Geothermal energy is a promising resource on Venus. The planet's intense internal heat could be harnessed to generate power. This geothermal energy could provide a stable and continuous source of electricity for colonies and robotic operations. The dense atmosphere of Venus offers opportunities for generating power through atmospheric harvesting. Wind turbines and other devices could capture the energy of the high-speed winds in the upper atmosphere, converting it into electricity. Sulfur, a key component of Venus's clouds, has numerous industrial applications. It can be used to produce sulfuric acid, which is essential for various chemical processes, and to manufacture fertilizers, batteries, and other products. Venus's surface is rich in silicates, which are the building blocks of glass and ceramics. These materials are crucial for constructing habitats and other infrastructure that can withstand the harsh surface conditions. The atmosphere of Venus also contains trace amounts of hydrogen and nitrogen. Hydrogen can be used as a fuel, while nitrogen is essential for creating a breathable atmosphere and for agricultural purposes. The carbon dioxide in Venus's atmosphere can be split into carbon and oxygen using solar-powered electrolysis. The oxygen can support life, while the carbon can be used to create carbon-based materials, essential for various construction and manufacturing processes. Venus's cloud layer, with its high-altitude winds, offers a unique environment for studying and potentially harvesting atmospheric electricity. This resource could be tapped using advanced technologies to provide power for high-altitude platforms and research stations. The high surface pressure on Venus could be used to our advantage in industrial processes. Certain chemical reactions that require high pressures could be conducted more efficiently on Venus, potentially leading to new manufacturing techniques. The surface rocks of Venus may contain radioactive elements like uranium and thorium. These materials could be used in nuclear reactors to provide a long-term energy source for colonies, assuming safe extraction and handling methods can be developed. The intense sunlight that reaches Venus's upper atmosphere can be harnessed using solar panels. This abundant solar energy is a key resource for powering both atmospheric platforms and surface installations. Exploring and utilizing the resources of Venus will require significant technological advancements. However, the potential rewards make Venus an intriguing target for future missions and long-term human presence. The development of these resources could support sustainable colonization and further our understanding of how to live and thrive in extreme environments. Reducing radiation exposure on Mars is critical for the safety and health of future astronauts. The thin atmosphere and lack of a magnetic field mean that Mars's surface is bombarded with harmful cosmic rays and solar radiation. One approach to mitigating radiation exposure is to build habitats underground. Living in lava tubes or creating subsurface bunkers can provide natural shielding from radiation. These structures use the Martian regolith as a protective barrier. Another method is to use Martian soil or regolith to create thick walls around surface habitats. This regolith can be compacted into bricks or used as a loose covering, significantly reducing radiation levels inside living areas. Water is an excellent radiation shield. Storing water in tanks around the habitat or within the walls can provide an additional layer of protection. This dual-purpose solution also ensures a ready supply of water for the crew. Advanced materials and coatings that absorb or deflect radiation can be used in the construction of habitats and spacesuits. These materials are being developed to offer lightweight yet effective protection against various types of radiation. Creating magnetic fields around habitats is another potential solution. By generating a localized magnetic field, it's possible to deflect charged particles away from living areas, mimicking Earth's natural protective magnetosphere. Radiation-hardened electronics and equipment are essential for any mission to Mars. These specially designed devices can withstand higher levels of radiation, ensuring the functionality of critical systems and instruments over long periods. Using Martian terrain features such as cliffs or large boulders as natural shields can also be effective. Placing habitats in these sheltered locations can reduce exposure to radiation from certain directions. Developing portable radiation shelters is important for astronauts working outside their main habitats. These shelters can provide immediate protection during solar storms or other periods of increased radiation activity. Monitoring radiation levels in real time allows astronauts to take timely protective measures. Equipping habitats and spacesuits with advanced radiation sensors helps track exposure and ensure safety protocols are followed. Implementing rigorous mission planning to minimize time spent outside protective habitats during high radiation periods is crucial. Understanding and predicting space weather patterns can help schedule activities during safer times. Medical research into countermeasures against radiation exposure is ongoing. Developing drugs or therapies that mitigate the effects of radiation on the human body could provide additional protection for astronauts. Leveraging robotics and automated systems to perform high-risk tasks outside habitats reduces human exposure to radiation. Robots can be used for construction, maintenance, and exploration, handling the most hazardous conditions. International collaboration in radiation research and technology development can accelerate the creation of effective solutions. Sharing knowledge and resources among space agencies and research institutions enhances our ability to protect future Mars explorers. Continued advancements in radiation protection technologies are essential for the success of long-term missions to Mars. Combining multiple strategies will provide the best defense against the harsh radiation environment, ensuring the safety and well-being of astronauts as we venture further into the solar system. Warming Mars to make it more habitable is a crucial step in the terraforming process. The current average temperature is around -80 degrees Fahrenheit, too cold for liquid water and human habitation. One proposed method to warm Mars is to introduce greenhouse gases into the atmosphere. These gases would trap heat from the sun, gradually raising the planet's temperature. Carbon dioxide, methane, and water vapor are among the gases that could be used. Using factories on Mars to produce these greenhouse gases is a viable approach. By building facilities that release these gases, we can initiate a controlled greenhouse effect. This process would require significant infrastructure, but is within the realm of possibility. Another idea is to deploy orbital mirrors or reflectors. These large structures could be positioned in space to reflect additional sunlight onto the Martian surface. The increased solar energy would help warm the planet directly. Terraforming efforts might also include blackening the polar ice caps. Dark materials spread over the ice would absorb more heat from the sun, causing the ice to melt and release carbon dioxide into the atmosphere, enhancing the greenhouse effect. Nuclear detonations in strategic locations have been suggested as a way to release carbon dioxide trapped in the Martian soil and ice. This method is controversial and poses significant risks, but it could rapidly increase atmospheric pressure and temperature. Building large arrays of solar panels to generate heat is another approach. These panels could collect and concentrate sunlight, creating localized warming that could spread over time. This method is safer and more controllable than other proposals. Genetically engineered organisms could play a role in warming Mars. These organisms might be designed to produce greenhouse gases as a byproduct of their metabolism. Introducing such life forms could help kickstart the warming process. Asteroid impacts are another potential method. Redirecting asteroids to collide with Mars would release significant amounts of energy, heating the atmosphere and surface. This method would also add mass and potentially beneficial materials to the planet. Creating artificial magnetic fields could help retain any newly thickened atmosphere. By protecting the atmosphere from solar wind, a magnetic field would prevent it from being stripped away, ensuring that warming efforts have a lasting effect. International collaboration and investment in technology are crucial for these warming efforts. Combining resources and expertise from different countries can accelerate progress and make large-scale projects more feasible. Research into the long-term effects of these warming methods is essential. Understanding how they might impact the Martian environment and potential ecosystems helps ensure that efforts to warm the planet do not lead to unforeseen consequences. Simulating warming methods in controlled environments on Earth can provide valuable insights. These simulations help refine techniques and predict outcomes, making actual implementation on Mars more effective and safer. Public engagement and support are vital for the success of terraforming projects. Educating people about the benefits and challenges of warming Mars can build the necessary backing for funding and long-term commitment. As we develop and refine methods to warm Mars, we move closer to transforming it into a habitable world. These efforts are part of a broader vision of expanding human presence in the solar system, ensuring our species' survival and prosperity in new environments. Creating a magnetic field on Mars is crucial for protecting the planet's atmosphere and future inhabitants from solar and cosmic radiation. Without a magnetic field, Mars is vulnerable to the solar wind stripping away its atmosphere, making long-term terraforming efforts challenging. One proposed method to generate a magnetic field on Mars is to use a large satellite in orbit around the planet. This satellite would generate a powerful magnetic field, providing protection for the atmosphere below. This concept involves significant engineering challenges, but is theoretically possible. Another idea is to create a series of artificial magnetic field generators on the Martian surface. These generators would work together to produce a coherent magnetic field strong enough to shield the planet from solar wind. This approach requires extensive infrastructure, but could be implemented in stages. Utilizing superconducting materials is essential for these magnetic field generators. Superconductors can carry large electric currents without resistance, making them ideal for creating strong magnetic fields. Advances in superconducting technology are critical for this approach. Another innovative idea is to induce a magnetic field by creating a molten iron core. This could be achieved by using nuclear reactors to heat Mars's core, causing it to circulate and generate a magnetic field similar to Earth's. This method is ambitious and would take a long time to implement. Alternatively, we could deploy a series of smaller, strategically placed satellites or ground stations to generate localized magnetic fields. These fields would overlap to provide broader coverage, offering incremental protection as more units are added. Using plasma torches to create a magnetic field is another concept under consideration. These torches would emit charged particles that create a magnetic field when directed properly. This method involves high energy costs but could be effective in the long run. Research into magnetic field generation also includes studying naturally magnetic materials on Mars. If deposits of these materials can be harnessed, they might contribute to a planet-wide magnetic field with less energy input. Creating a magnetic field is not just about technology. It also involves understanding and mitigating the potential impacts on the Martian environment. Any method chosen must ensure that it does not disrupt the planet's delicate balance or future ecosystems. International collaboration is essential for creating a magnetic field on Mars. Sharing resources, expertise, and technology can make this ambitious project more feasible. Joint efforts can also distribute the financial and logistical burdens. Testing magnetic field generation methods in space environments closer to Earth can provide valuable insights. These tests help refine techniques and address challenges before deploying them on Mars. Public support and investment in research and development are crucial. Educating people about the importance of a magnetic field for Mars's habitability can build the necessary backing for sustained funding and interest. Integrating magnetic field generation with other terraforming efforts is important for a cohesive strategy. Ensuring that atmosphere creation, temperature regulation, and radiation protection work together harmoniously will enhance the overall success of terraforming Mars. As we advance our understanding and capabilities in magnetic field generation, we move closer to making Mars a viable home for future generations. This effort represents a significant step in our journey to become a multiplanetary species. Creating a magnetic field on Mars is one of the most complex challenges in terraforming, but with continued innovation and collaboration, it is a challenge we can overcome. The success of this endeavor will pave the way for humanity's expansion into the cosmos, ensuring our survival and growth beyond Earth. Introducing microorganisms to Mars is a critical step in the terraforming process. These microorganisms can help transform the Martian environment by producing oxygen, breaking down toxic chemicals, and creating fertile soil for plants. One of the primary goals is to introduce cyanobacteria. These bacteria can photosynthesize, using sunlight to convert carbon dioxide into oxygen. This process could gradually increase the oxygen levels in the Martian atmosphere, making it more suitable for human life. Microorganisms can also help in nitrogen fixation. Certain bacteria can convert nitrogen from the atmosphere into ammonia, which is a form of nitrogen that plants can use. This process is essential for creating a viable ecosystem on Mars. Fungi play a crucial role in breaking down organic material and enriching the soil. Introducing fungi that can decompose Martian regolith and create nutrient-rich soil would support the growth of plants and other organisms. Extremophiles, microorganisms that thrive in extreme conditions, are ideal candidates for introduction to Mars. These organisms can survive the harsh Martian environment, including high radiation levels, low temperatures, and arid conditions. The process of bioremediation involves using microorganisms to clean up toxic substances in the environment. On Mars, this could mean breaking down perchlorates in the soil, which are harmful to humans and plants. Genetically engineered microorganisms can be designed to perform specific functions, such as producing greenhouse gases to warm the planet or secreting substances that bind the soil and prevent dust storms. Microorganisms can also help in water purification. Introducing bacteria that can filter and purify water sources on Mars would be essential for providing clean water for human consumption and agriculture. Research on Earth in extreme environments, such as Antarctica and deep-sea hydrothermal vents, provides valuable insights into which microorganisms might thrive on Mars. These studies help scientists select and prepare the best candidates for introduction. Field tests in Martian analog environments, such as the Atacama Desert or Arctic permafrost, allow researchers to simulate the conditions on Mars and observe how microorganisms perform. These tests are crucial for refining strategies before deployment. Careful monitoring and control of introduced microorganisms are essential to prevent unintended ecological consequences. Scientists must ensure that these organisms do not disrupt any existing Martian ecosystems or outcompete each other in ways that could hinder the terraforming process. Introducing microorganisms is a gradual process that requires patience and long-term planning. The goal is to create a self-sustaining biosphere that can support higher forms of life, including plants, animals, and eventually humans. Public engagement and education are important to gain support for these efforts. Informing people about the benefits and challenges of introducing microorganisms to Mars can build the necessary backing for continued research and development. International collaboration is crucial for the successful introduction of microorganisms. Sharing knowledge, resources, and technology can accelerate progress and ensure that efforts are coordinated and effective. As we advance in our ability to introduce and manage microorganisms on Mars, we move closer to transforming the planet into a habitable world. This effort represents a significant milestone in humanity's journey to becoming an interplanetary species, capable of thriving on multiple worlds. Establishing human habitats on Mars is a monumental task that involves numerous challenges and innovative solutions. The first step is to select the right location, considering factors like access to water, sunlight, and protection from radiation. Initial habitats will likely be constructed from prefabricated modules transported from Earth. These modules must be designed to withstand Mars's harsh conditions, including extreme temperatures, high radiation levels, and dust storms. Underground habitats offer natural protection from radiation and extreme temperatures. Building homes in lava tubes or creating artificial caves can provide a safer living environment for the first settlers. Using Martian resources to build habitats is essential for long-term sustainability. In situ resource utilization, or ISRU, involves using materials found on Mars, such as regolith, to create building materials like bricks and cement. Habitat design must prioritize life support systems that provide air, water, and food. Recycling systems will be crucial, ensuring that waste products are converted back into usable resources to support a closed-loop ecosystem. Greenhouses will be vital for growing food and producing oxygen. These structures need to be highly efficient, using hydroponics or aeroponics to maximize crop yields with minimal water usage. Energy production is a critical aspect of establishing habitats. Solar panels are the most viable option, but they must be designed to withstand dust accumulation and harsh weather conditions. Backup power systems, such as small nuclear reactors, may also be necessary. Radiation protection extends beyond living quarters. Spacesuits must provide adequate shielding for astronauts working outside, and transportation vehicles need to be designed with protective materials to ensure safe travel across the Martian surface. Creating a comfortable living environment is essential for the mental health of settlers. Habitats should include communal areas, recreational facilities, and private spaces to support the well-being and productivity of the inhabitants. Communication systems must be robust and reliable, providing constant contact with Earth. This includes not only scientific data transmission, but also personal communication to keep settlers connected with family and friends. Healthcare facilities will be necessary to address medical needs. These facilities must be equipped to handle emergencies, provide routine care, and manage the unique health challenges posed by living on Mars, such as the effects of low gravity on the human body. Transportation infrastructure will evolve as settlements grow. Initially, rovers will be the primary means of transport, but over time, more advanced vehicles, including aerial drones and eventually aircraft, will facilitate movement across the planet. International collaboration can enhance the success of human habitats on Mars. Sharing technology, knowledge, and resources among spacefaring nations can lead to more efficient and effective solutions for establishing and maintaining settlements. Education and training for settlers are crucial. Astronauts and future colonists must be well versed in a wide range of skills, from operating life support systems to conducting scientific research and repairing habitat infrastructure. As we establish human habitats on Mars, we lay the foundation for a new chapter in human history. These efforts not only represent a significant technological and scientific achievement, but also embody the spirit of exploration and our quest to extend humanity's reach into the cosmos. Thickening the atmosphere on Mars is essential for creating a more hospitable environment. A denser atmosphere would help retain heat, support liquid water, and provide better protection from radiation. One method to thicken the atmosphere is to release greenhouse gases. These gases, such as carbon dioxide and methane, can trap heat from the sun, gradually warming the planet and increasing atmospheric pressure. Carbon dioxide can be released from the Martian soil and polar ice caps. Heating these areas using solar mirrors or nuclear detonations could release significant amounts of CO2, contributing to atmospheric thickening. Introducing plants and microorganisms that produce oxygen and other gases through photosynthesis is another approach. These organisms would not only help thicken the atmosphere but also increase oxygen levels, making it more breathable for humans. Artificial methods, such as factories that produce greenhouse gases, can be established on Mars. These facilities would continuously release gases into the atmosphere, accelerating the thickening process. Using asteroids to deliver volatile compounds is another innovative idea. Redirecting icy asteroids to impact Mars could release water vapor and other gases, adding to the atmosphere and increasing pressure. Maintaining the increased atmospheric pressure is crucial. Creating a magnetic field around Mars can help protect the thickened atmosphere from being stripped away by solar wind. International collaboration and shared resources are essential for these large-scale projects. Combining efforts and expertise from multiple countries can make the process more efficient and feasible. Advanced technology and materials will play a significant role in thickening Mars's atmosphere. Continued research and development are necessary to refine methods and ensure their effectiveness. Simulating the thickening process on Earth in controlled environments provides valuable data. These simulations help scientists predict outcomes and address potential challenges before implementing them on Mars. Public engagement and support are vital for the success of these endeavors. Educating people about the benefits and challenges of thickening Mars's atmosphere can build the necessary backing for sustained funding and commitment. Monitoring and adjusting the thickening process are crucial to avoid unintended consequences. Continuous observation and research will help scientists fine-tune methods and ensure a balanced and stable atmosphere. Developing infrastructure to support the thickened atmosphere, such as advanced habitats and life support systems, is essential. These systems must be designed to function effectively in the new environmental conditions. Thickening the atmosphere is a long-term endeavor that requires patience and perseverance. It represents a significant step toward making Mars a viable home for future generations, supporting human life and expanding our presence in the solar system. As we progress in thickening Mars's atmosphere, we move closer to transforming the planet into a new frontier for humanity. This monumental effort exemplifies our commitment to exploration, innovation, and the enduring quest to extend our reach beyond Earth. Water extraction and distribution on Mars is crucial for sustaining human life and supporting agricultural and industrial activities. The presence of water ice at the polar caps and beneath the surface offers a valuable resource for future missions. One method for extracting water is to mine the ice from the polar caps. This involves using robotic drills and heaters to melt the ice and pump the water to the surface. This process can provide a steady supply of water for various uses. Subsurface ice deposits can also be accessed by drilling into the Martian soil. These drills can reach the ice layers, melt them, and extract the water. This method allows for the tapping of water reserves that are more widespread across the planet. Hydrated minerals in the Martian soil are another potential water source. These minerals can be heated to release the water they contain. This technique requires advanced technology to identify and process the minerals efficiently. Once extracted, the water needs to be purified to remove any contaminants. Filtration systems and chemical treatments ensure that the water is safe for drinking, cooking, and other uses. Purification is a critical step in maintaining the health and safety of settlers. Storing the extracted water is essential for managing the supply. Tanks and reservoirs can be built to hold the water, providing a buffer against any disruptions in extraction processes. These storage systems must be designed to prevent contamination and loss. A distribution network is necessary to transport water from extraction sites to habitats and agricultural areas. Pipelines, pumps, and valves form the backbone of this network, ensuring that water reaches all necessary locations efficiently. Recycling water within habitats is vital for conservation. Grey water and wastewater treatment systems can purify and reuse water, reducing the need for constant extraction. These systems help create a sustainable, closed-loop water cycle. Agricultural areas on Mars will require a reliable water supply for growing crops. Irrigation systems must be developed to deliver water efficiently to plants, using techniques like drip irrigation to minimize waste and maximize yield. Water is also essential for producing fuel. Electrolysis can split water into hydrogen and oxygen, which can be used as rocket propellants. This process supports return missions to Earth and further exploration of the solar system. Monitoring water usage and distribution helps manage this precious resource effectively. Sensors and control systems provide real-time data on water levels, consumption rates, and potential leaks, ensuring efficient use and quick response to issues. Research into alternative water extraction methods continues to advance. Innovations like atmospheric water capture, which extracts moisture from the air, could provide additional sources of water in the future. International collaboration can enhance water extraction and distribution efforts. Sharing knowledge, technology, and resources can lead to more effective solutions and a reliable water supply for all missions. Public support and investment in water extraction technology are crucial. Educating people about the importance of water resources on Mars can build the necessary backing for continued research and development. As we develop and implement water extraction and distribution systems on Mars, we take significant steps toward creating a sustainable human presence on the planet. Access to water is fundamental for life, making these efforts essential for the success of future colonization. Mars soil fertilization is essential for growing crops and supporting sustainable agriculture on the planet. The Martian regolith, while rich in some minerals, lacks the organic matter and nutrients needed for plant growth. One of the first steps in fertilizing Martian soil is to add organic matter. Composting human waste, plant debris, and other organic materials can create nutrient-rich compost. This compost can be mixed with the Martian soil to improve its fertility. Introducing microorganisms that can break down organic matter is also crucial. These microbes decompose organic materials, releasing nutrients that plants can absorb. They play a vital role in creating a healthy soil ecosystem. Biochar, a form of charcoal produced from organic waste, can be added to Martian soil to improve its structure and nutrient holding capacity. Biochar can help retain water and nutrients, making them more available to plants. Nitrogen is a critical nutrient for plant growth, but it is scarce in Martian soil. Nitrogen-fixing bacteria can be introduced to convert atmospheric nitrogen into forms that plants can use. These bacteria are essential for creating a self-sustaining nitrogen cycle. Phosphorus and potassium are also essential nutrients that are lacking in Martian soil. These elements can be supplied through mineral fertilizers or by processing Martian rocks that contain them. Ensuring a balanced supply of these nutrients is crucial for healthy plant growth. Hydroponics and aeroponics are alternative methods for growing plants without soil. These systems use nutrient-rich water solutions to provide plants with everything they need. They can be used alongside soil-based methods to maximize agricultural productivity. Developing soil additives from local Martian resources is another approach. For example, basalt rock dust can be added to the soil to provide trace minerals and improve its physical properties. Utilizing local materials reduces the need for imports from Earth. Testing and monitoring soil health is essential for successful fertilization. Sensors and analytical tools can measure nutrient levels, pH, and other soil properties. This data helps adjust fertilization strategies to ensure optimal conditions for plant growth. Crop rotation and companion planting are agricultural practices that can enhance soil fertility. By rotating different crops and planting mutually beneficial species together, the soil can be enriched and its health maintained over time. Water management is closely linked to soil fertilization. Efficient irrigation techniques, such as drip irrigation, ensure that water reaches plant roots without causing erosion or nutrient leaching. Proper water management supports healthy soil and plant growth. Research into Martian soil and its properties is ongoing. Understanding the soil's composition, structure, and potential contaminants helps develop effective fertilization methods. Continuous research is vital for improving agricultural practices on Mars. International collaboration can enhance soil fertilization efforts. Sharing knowledge, resources, and technology can lead to innovative solutions and more effective soil management practices. Global cooperation is key to successful Mars colonization. Public support and investment in soil fertilization technology are crucial. Educating people about the importance of fertile soil for sustainable agriculture on Mars can build the necessary backing for continued research and development. As we develop and implement soil fertilization techniques on Mars, we take significant steps toward creating a sustainable food supply. Fertile soil is the foundation of agriculture, making these efforts essential for the success of future human settlements on the planet. Mars plant growth and agriculture are pivotal for sustaining human life and creating self-sufficient colonies. Establishing effective agricultural systems ensures a continuous food supply, reducing dependence on Earth. Greenhouses will be the primary structures for growing plants on Mars. These controlled environments protect crops from harsh conditions, regulate temperature, and provide adequate light for photosynthesis. LED lighting can supplement sunlight in greenhouses. By using specific wavelengths, LED lights can enhance plant growth and increase yields, ensuring crops receive optimal light conditions year-round. Hydroponic systems, which use nutrient-rich water instead of soil, are ideal for Mars. These systems allow precise control over nutrient delivery, reduce water usage, and can be set up in compact spaces, maximizing the use of available area. Aeroponics, where plant roots are suspended in the air and misted with nutrient solutions, is another efficient method. This technique promotes rapid growth and high yields, using even less water than hydroponics. Selecting the right crops is essential for Martian agriculture. Fast-growing, high-yield plants like potatoes, carrots, and leafy greens provide essential nutrients and can thrive in controlled environments. Variety ensures a balanced diet for settlers. Companion planting can enhance crop productivity. Planting mutually beneficial species together can improve pest resistance, soil health, and overall yield. This practice creates a more resilient agricultural system. Developing crops that can withstand Martian conditions is a focus of genetic engineering. Scientists are working to create plants that can tolerate lower temperatures, high radiation, and reduced gravity, making them suitable for growth on Mars. Soil-based agriculture will also play a role. By enhancing Martian soil with compost, biochar, and other amendments, we can create fertile ground for growing a wider range of crops. This approach integrates local resources with advanced agricultural techniques. Water recycling is crucial for sustainable agriculture. Systems that purify and reuse water from plant transpiration and other sources ensure that every drop is utilized efficiently, maintaining a consistent supply for crops. Pollination must be managed in Martian greenhouses. While some plants are self-pollinating, others require insects or manual pollination. Introducing pollinators like bees or using robotic pollinators can ensure successful crop reproduction. Climate control within greenhouses involves regulating temperature, humidity, and carbon dioxide levels. Advanced climate control systems can create ideal conditions for plant growth, mimicking Earth's environments as closely as possible. Nutrient cycling in agricultural systems is vital. By composting plant waste and using it to enrich the soil, we create a closed-loop system that minimizes waste and maximizes resource efficiency, supporting long-term sustainability. Agricultural research on Mars will continue to evolve. Experimental greenhouses and farms will test different methods and crops, providing data to improve practices and increase productivity. Continuous learning is essential for adapting to Mars's unique challenges. Building a robust agricultural system on Mars not only supports human life but also represents a significant step towards self-sufficiency. Successful agriculture will enable colonies to thrive independently, fostering a new era of human exploration and settlement in the solar system. Achieving long-term ecological stability on Mars is essential for sustaining human settlements and ensuring a thriving environment. This involves creating self-sustaining ecosystems that can support diverse forms of life over extended periods. A key component of ecological stability is biodiversity. Introducing a variety of plant and animal species can create a balanced ecosystem. Each species plays a specific role, contributing to nutrient cycling, soil health, and overall ecological resilience. Maintaining soil fertility is crucial for long-term stability. Continuous composting, crop rotation, and the use of green manures can replenish nutrients in the soil, ensuring that it remains productive for agriculture. Water management is vital for sustaining life on Mars. Efficient recycling systems, water-saving irrigation techniques, and careful monitoring of water sources help ensure a reliable supply for both human use and agriculture. Energy sustainability is another critical factor. Renewable energy sources like solar and wind power must be harnessed and optimized to provide continuous power for habitats, greenhouses, and other infrastructure. Waste management systems are essential for ecological stability. Recycling and reusing materials, composting organic waste, and safely disposing of non-recyclable waste help maintain a clean and healthy environment. Establishing and maintaining climate control within habitats and greenhouses is necessary for stability. Regulating temperature, humidity, and atmospheric composition ensures that conditions remain conducive to life. Pollution control measures must be in place to prevent contamination of air, water, and soil. Minimizing the release of harmful substances and using clean technologies contribute to a healthier ecosystem. Regular environmental monitoring is crucial. Tracking changes in soil health, water quality, air composition, and biodiversity helps identify potential issues early and allows for timely interventions to maintain stability. Integrating local resources into ecological systems enhances sustainability. Utilizing Martian soil, water, and minerals reduces the need for imports from Earth and helps create a self-sufficient settlement. Developing closed-loop systems where waste products are repurposed into useful resources supports long-term ecological health. For example, converting organic waste into compost or biofuel ensures efficient use of available materials. Research into the interactions between different species and environmental conditions on Mars is essential. Understanding these dynamics helps optimize ecosystem design and management, promoting long-term stability. International collaboration in ecological research and resource management can enhance the effectiveness of these efforts. Sharing knowledge, technologies, and best practices ensures a more robust and resilient ecological system. Public engagement and education about the importance of ecological stability can build support for sustainable practices. Involving settlers in environmental stewardship fosters a culture of sustainability and responsibility. As we work towards long-term ecological stability on Mars, we lay the foundation for enduring human presence and expansion into the cosmos. These efforts ensure that future generations can thrive in a balanced and self-sustaining environment, embodying our commitment to sustainable exploration and settlement. Cooling Venus is a significant challenge due to its extreme surface temperatures, averaging around 900 degrees Fahrenheit. Achieving a cooler environment is essential for making the planet more hospitable for human habitation and potential colonization. One proposed method for cooling Venus is to use giant reflective mirrors in space. These mirrors would reduce the amount of sunlight reaching the planet's surface, thereby lowering temperatures over time. This concept involves significant engineering and logistical challenges but offers a feasible solution. Another approach is to introduce reflective aerosols into Venus's atmosphere. These particles would increase the planet's albedo, reflecting more sunlight back into space. Similar to how volcanic eruptions on Earth can lead to temporary cooling, this method could help reduce surface temperatures on Venus. Creating a series of sunshades or solar sails in orbit around Venus is another idea. These structures would block a portion of the sunlight, gradually cooling the planet. This method requires advanced materials and precise deployment to be effective. Altering the atmospheric composition of Venus is crucial for cooling the planet. Reducing the levels of carbon dioxide, which constitutes 96.5% of the atmosphere, would lessen the greenhouse effect. One way to achieve this is by sequestering carbon dioxide into solid carbonates or other stable compounds. Introducing microorganisms that can convert carbon dioxide into oxygen is another potential solution. Genetically engineered bacteria could be released into the atmosphere to initiate this process. Over time, this biological approach could significantly alter the atmospheric composition. Using chemical reactions to convert carbon dioxide into less harmful gases is also being explored. For instance, reacting CO2 with certain minerals could produce carbonates and release oxygen, helping to cool the planet and create a more breathable atmosphere. Terraforming Venus could also involve geoengineering techniques to enhance heat dissipation. Installing heat exchangers on the planet's surface could facilitate the transfer of heat from the ground to the upper atmosphere, where it can radiate into space more effectively. Altering the planet's rotation to increase the length of its day could help regulate temperatures. This is an extremely ambitious and theoretical approach, involving massive external forces to change Venus's rotational dynamics, but it could contribute to a more stable climate. Removing the thick cloud layers of sulfuric acid is another cooling strategy. These clouds trap heat, and reducing their density could allow more heat to escape into space. This could be achieved through chemical processes that break down sulfuric acid into less harmful components. Developing advanced materials that can withstand Venus's harsh conditions is essential for any cooling infrastructure. These materials would need to be highly durable and capable of functioning effectively in extreme temperatures and pressures. International collaboration and investment in cooling technologies are crucial. Combining resources and expertise from multiple countries can accelerate progress and make large-scale geoengineering projects more feasible. Continuous monitoring of Venus's climate and atmospheric conditions is necessary to track the progress of cooling efforts. Advanced sensors and satellites can provide real-time data, helping scientists make informed decisions and adjustments. Public engagement and support for cooling initiatives are important. Educating people about the potential benefits and challenges of cooling Venus can build the necessary backing for sustained research and development. As we develop and implement methods to cool Venus, we take significant steps toward transforming the planet into a more habitable environment. These efforts represent a bold vision for the future, where human ingenuity and technological innovation enable us to overcome the most formidable planetary challenges. Reducing the atmospheric pressure on Venus is essential for making the planet habitable. Currently, the surface pressure is about 92 times that of Earth, equivalent to being 3,000 feet underwater. This extreme pressure poses significant challenges for human habitation and technological operations. One method to reduce atmospheric pressure is by removing carbon dioxide, which makes up 96.5% of the atmosphere. Sequestering CO2 into solid carbonates through chemical reactions is a potential approach. This process would involve converting gaseous carbon dioxide into solid minerals, reducing the overall atmospheric mass. Deploying large-scale scrubbers or factories that can extract and sequester carbon dioxide is another strategy. These facilities would operate continuously to capture and store CO2, gradually lowering atmospheric pressure over time. Introducing photosynthetic microorganisms is another potential solution. Genetically engineered bacteria or algae that can convert carbon dioxide into oxygen could be released into the atmosphere. This biological approach would help reduce CO2 levels while increasing oxygen, making the atmosphere more breathable. Chemical reactions using readily available materials on Venus can also help. For example, reacting CO2 with calcium or magnesium compounds to form stable carbonates can effectively reduce atmospheric pressure. These reactions would need to be scaled up significantly to have a noticeable impact. Creating giant solar reflectors in orbit around Venus could reduce the amount of sunlight reaching the planet, cooling the surface and potentially lowering atmospheric pressure. These reflectors would need to be precisely positioned and maintained. Reducing the density of the sulfuric acid clouds in Venus's upper atmosphere can also help. These clouds trap heat and contribute to the high surface pressure. Breaking down sulfuric acid into less dense compounds could allow more heat to escape and reduce pressure. Technological advancements in materials science are crucial for developing equipment that can withstand Venus's current conditions while working to reduce atmospheric pressure. Durable, heat-resistant materials will be essential for any machinery or infrastructure deployed on the planet. International collaboration and funding are vital for the success of these large-scale geoengineering projects. Pooling resources and expertise from multiple countries can accelerate the development and implementation of effective pressure reduction technologies. Continuous monitoring of atmospheric changes on Venus is necessary to track progress and make adjustments. Advanced sensors and satellites can provide real-time data, ensuring that efforts are moving in the right direction and allowing for timely interventions if needed. And public support and understanding of these efforts are crucial. Educating people about the importance and challenges of reducing Venus's atmospheric pressure can build the necessary backing for long-term research and investment. Developing and testing prototypes on Earth or in space can provide valuable insights before full-scale deployment on Venus. These tests help refine techniques and address potential issues in controlled environments. As atmospheric pressure decreases, it will be important to evaluate and mitigate any unintended ecological impacts. Ensuring that these efforts do not harm potential native life forms or disrupt the planet's natural processes is a critical consideration. Achieving a significant reduction in atmospheric pressure on Venus will likely be a long-term endeavor, requiring decades or even centuries of sustained effort. Patience and perseverance will be essential for success. As we work towards reducing Venus's atmospheric pressure, we take crucial steps toward transforming the planet into a more habitable environment. These efforts reflect humanity's determination to explore and adapt, pushing the boundaries of what is possible in our quest to expand into the cosmos. Removing excess carbon dioxide from Venus's atmosphere is critical for making the planet habitable. The dense CO2 atmosphere creates extreme surface pressure and temperature, both of which need to be mitigated. One potential method for removing CO2 is through chemical sequestration. This involves converting carbon dioxide into solid carbonates using chemical reactions with minerals like calcium or magnesium. These solid carbonates could then be stored on the surface or underground. Deploying large-scale carbon capture plants on Venus could help reduce CO2 levels. These plants would extract carbon dioxide from the atmosphere and convert it into useful compounds or store it safely. Advanced technologies and materials would be required to build and operate these plants in Venus's harsh conditions. Using solar-powered machines to split carbon dioxide into carbon and oxygen is another approach. These machines would use concentrated solar energy to drive the chemical reactions needed to break down CO2, effectively reducing its concentration in the atmosphere. Introducing genetically engineered microorganisms that can consume carbon dioxide and produce oxygen is a biological solution. These microorganisms could be spread throughout the atmosphere or cultivated in controlled environments to maximize their impact on CO2 levels. Transporting CO2 off-planet using space elevators or rockets is a more radical approach. This method involves capturing carbon dioxide and launching it into space or redirecting it to other locations, significantly reducing atmospheric pressure over time. Artificial photosynthesis technologies could also be deployed. These systems mimic natural photosynthesis, using light to convert carbon dioxide and water into glucose and oxygen. Scaled-up versions of these systems could contribute to significant reductions in CO2 levels. Research into advanced catalysts that can efficiently convert CO2 into less harmful gases is ongoing. These catalysts would be used in industrial processes on Venus, turning carbon dioxide into substances like methane or water vapor, which have less impact on atmospheric pressure and temperature. Developing reflective materials that can be spread over the surface to reduce heat absorption and indirectly reduce CO2 levels is another innovative idea. These materials would reflect more sunlight away from the planet, cooling it and slowing the release of carbon dioxide from surface materials. Using robotic systems to mine and process carbon-rich rocks on Venus can also help. These robots would extract carbon from the rocks and store it in stable forms, gradually lowering the atmospheric CO2 concentration. International collaboration is essential for tackling this enormous challenge. Pooling resources, expertise, and technology from multiple countries can accelerate the development and implementation of effective CO2 removal strategies. Continuous monitoring of the atmosphere is crucial for assessing the effectiveness of CO2 removal methods. Advanced satellites and sensors can track changes in atmospheric composition, providing real-time data to guide ongoing efforts. Public support and education about the importance of removing excess carbon dioxide are vital. Engaging the global community and securing long-term investment in research and development can ensure sustained progress. Testing these technologies on Earth or in controlled environments will help refine methods and address potential challenges before deploying them on Venus. Successful trials can build confidence in the feasibility of large-scale CO2 removal. As we advance in removing excess carbon dioxide from Venus's atmosphere, we move closer to transforming the planet into a more livable environment. These efforts represent a significant step in our quest to extend human presence beyond Earth and create new homes in the solar system. Introducing microorganisms to Venus is a critical step in transforming its atmosphere and surface. These microorganisms can help break down toxic compounds, produce oxygen, and create a more habitable environment. The first type of microorganisms to introduce are extremophiles, which thrive in extreme conditions. These organisms can survive Venus's high temperatures and acidic atmosphere, making them ideal pioneers for terraforming efforts. Cyanobacteria are a key group of microorganisms for Venus. They can photosynthesize, using sunlight to convert carbon dioxide into oxygen. This process not only reduces CO2 levels, but also increases the oxygen concentration, making the atmosphere more breathable. Another beneficial microorganism is acidophiles. These bacteria thrive in acidic environments and can help neutralize the sulfuric acid in Venus's atmosphere. By breaking down sulfuric acid, they contribute to lowering the planet's overall acidity. Introducing genetically engineered bacteria can accelerate the transformation process. These bacteria can be designed to perform specific functions, such as enhancing CO2 sequestration or producing essential nutrients for future plant life. Bioreactors can be used to cultivate and release these microorganisms in a controlled manner. These devices would ensure that the microorganisms are introduced gradually and in the right quantities to maximize their effectiveness. Microorganisms can also play a role in soil formation on Venus. By breaking down rocks and minerals, they create the first layers of soil, which are essential for supporting plant life in the future. Another important function of microorganisms is nitrogen fixation. Certain bacteria can convert atmospheric nitrogen into ammonia, a form of nitrogen that plants can use. This process is crucial for creating a fertile environment on Venus. Monitoring the growth and spread of introduced microorganisms is essential. Using advanced sensors and satellites, scientists can track their progress and ensure that they are thriving and performing their intended functions. It's important to study the potential ecological impacts of introducing microorganisms. Ensuring that these organisms do not harm any existing ecosystems or create new problems is a critical aspect of the terraforming process. Collaboration with international scientists and researchers can enhance the effectiveness of introducing microorganisms. Sharing knowledge and resources can lead to more innovative solutions and successful implementation. Public engagement and support for these efforts are crucial. Educating people about the benefits and challenges of introducing microorganisms to Venus can build the necessary backing for long-term research and development. Testing the introduction of microorganisms in controlled environments on Earth or in space can provide valuable insights. These tests help refine methods and address potential issues before full-scale deployment on Venus. Developing advanced technologies to transport and release microorganisms on Venus is another critical aspect. Ensuring that they survive the journey and can be effectively distributed in the harsh Venusian environment is essential for success. As we progress in introducing microorganisms to Venus, we move closer to creating a more hospitable planet. These efforts are a significant step in the long journey of terraforming Venus, reflecting humanity's determination to explore and adapt to new worlds. Establishing floating habitats on Venus offers a unique solution to the planet's extreme surface conditions. These habitats would reside in the upper atmosphere, where temperatures and pressures are more Earth-like. Floating habitats would be constructed using lightweight, durable materials capable of withstanding the acidic environment. These materials must be resistant to corrosion and capable of supporting life support systems. Helium or hydrogen could be used to provide buoyancy for these habitats. Large balloon-like structures filled with these gases would allow the habitats to float at the desired altitude, approximately 50 kilometers above the surface. These habitats would need advanced life support systems to maintain a stable, breathable atmosphere inside. This includes systems for oxygen production, carbon dioxide removal, and temperature regulation. Energy for the habitats could be harnessed from the abundant sunlight available in Venus's upper atmosphere. Solar panels would be an effective way to generate electricity for all the necessary systems and equipment. Water could be harvested from the atmosphere. Venus's clouds contain trace amounts of water vapor, which can be extracted and purified for drinking, cooking, and other uses. Efficient water recycling systems would also be crucial. Growing food in floating habitats is essential for sustainability. Hydroponic and aeroponic systems can be used to grow crops without soil, providing fresh food for inhabitants and contributing to oxygen production. Communications infrastructure must be robust to maintain contact with Earth and other habitats. Satellite systems and high-frequency radio communications would ensure reliable connectivity for data transmission and personal communication. Safety measures for dealing with potential hazards, such as storms or atmospheric turbulence, are crucial. The habitats must be designed to withstand and respond to sudden changes in atmospheric conditions. The habitats would need facilities for research and exploration. Scientists could study Venus's atmosphere, climate, and potential resources from the safety of the floating habitats, advancing our understanding of the planet. Recreation and living spaces should be designed to support the mental and physical well-being of inhabitants. Comfortable living quarters, communal areas, and spaces for exercise and relaxation are essential for long-term missions. Robotic drones and probes can be deployed from the floating habitats to explore the surface and lower atmosphere of Venus. These robots would conduct scientific experiments and gather data without exposing humans to the extreme conditions. International collaboration on floating habitats can enhance technological development and resource sharing. Combining efforts from multiple countries ensures a more effective and sustainable approach to establishing a presence on Venus. Public engagement and education about the potential of floating habitats can generate interest and support for these ambitious projects. Highlighting the scientific and exploratory benefits can build the necessary backing for continued investment. As we progress in developing and deploying floating habitats on Venus, we take significant steps toward expanding human presence beyond Earth. These efforts showcase human ingenuity and resilience, paving the way for future exploration and potential colonization of one of our closest planetary neighbors. Creating a magnetic field on Venus is crucial for protecting the atmosphere and future habitats from solar and cosmic radiation. Without a magnetic field, Venus remains vulnerable to the solar wind stripping away its atmosphere. One method to generate a magnetic field is to use a large satellite in orbit around Venus. This satellite would generate a powerful magnetic field, providing protection for the atmosphere below. This concept involves significant engineering challenges, but offers a feasible solution. Another approach is to create a series of artificial magnetic field generators on the surface of Venus. These generators would work together to produce a coherent magnetic field strong enough to shield the planet from solar wind. This approach requires extensive infrastructure, but could be implemented in stages. Utilizing superconducting materials is essential for these magnetic field generators. Superconductors can carry large electric currents without resistance, making them ideal for creating strong magnetic fields. Advances in superconducting technology are critical for this approach. Another innovative idea is to induce a magnetic field by creating a molten iron core. This could be achieved by using nuclear reactors to heat Venus's core, causing it to circulate and generate a magnetic field similar to Earth's. This method is ambitious and would take a long time to implement. Alternatively, we could deploy a series of smaller, strategically placed satellites or ground stations to generate localized magnetic fields. These fields would overlap to provide broader coverage, offering incremental protection as more units are added. Using plasma torches to create a magnetic field is another concept under consideration. These torches would emit charged particles that create a magnetic field when directed properly. This method involves high energy costs, but could be effective in the long run. Research into magnetic field generation also includes studying naturally magnetic materials on Venus. If deposits of these materials can be harnessed, they might contribute to a planet-wide magnetic field with less energy input. Creating a magnetic field is not just about technology. It also involves understanding and mitigating the potential impacts on the Venusian environment. Any method chosen must ensure that it does not disrupt the planet's delicate balance or future ecosystems. International collaboration is essential for creating a magnetic field on Venus. Sharing resources, expertise, and technology can make this ambitious project more feasible. Joint efforts can also distribute the financial and logistical burdens. Testing magnetic field generation methods in space environments closer to Earth can provide valuable insights. These tests help refine techniques and address challenges before deploying them on Venus. Public support and investment in research and development are crucial. Educating people about the importance of a magnetic field for Venus's habitability can build the necessary backing for sustained funding and interest. Integrating magnetic field generation with other terraforming efforts is important for a cohesive strategy. Ensuring that atmosphere creation, temperature regulation, and radiation protection work together harmoniously will enhance the overall success of terraforming Venus. As we advance our understanding and capabilities in magnetic field generation, we move closer to making Venus a viable home for future generations. This effort represents a significant step in our journey to become a multiplanetary species. Creating a magnetic field on Venus is one of the most complex challenges in terraforming. But with continued innovation and collaboration, it is a challenge we can overcome. The success of this endeavor will pave the way for humanity's expansion into the cosmos, ensuring our survival and growth beyond Earth. Regulating the atmosphere on Venus is essential for making the planet habitable. The current atmosphere is composed mainly of carbon dioxide, with clouds of sulfuric acid, creating extreme greenhouse conditions. One of the first steps in regulating the atmosphere is to reduce the carbon dioxide levels. This can be achieved through chemical sequestration, converting CO2 into solid carbonates that can be stored on the surface or underground. Introducing photosynthetic microorganisms, such as genetically engineered cyanobacteria, can help convert carbon dioxide into oxygen. This biological approach can gradually change the atmospheric composition, making it more suitable for human life. Another method is to use large-scale machines to capture and store carbon dioxide. These machines would extract CO2 from the atmosphere and convert it into useful compounds or store it safely, reducing the overall atmospheric pressure. Deploying reflective aerosols in the upper atmosphere can help cool the planet by increasing its albedo. These particles reflect sunlight back into space, reducing the amount of heat that reaches the surface. Using orbital mirrors or sunshades to block a portion of the sunlight can also help regulate the temperature. These structures would need to be positioned precisely to effectively reduce the heat reaching Venus's surface. Breaking down sulfuric acid in the clouds is another important step. Chemical reactions that convert sulfuric acid into less harmful compounds can reduce the planet's acidity and make the atmosphere more hospitable. Advanced materials and technologies will be essential for these processes. Developing corrosion-resistant materials and efficient chemical processes is critical for operating in Venus's harsh environment. International collaboration is vital for the success of these large-scale atmospheric regulation projects. Pooling resources, expertise, and technology from multiple countries can accelerate progress and make these ambitious goals achievable. Continuous monitoring of the atmospheric changes is crucial. Advanced satellites and sensors can provide real-time data on atmospheric composition and temperature, ensuring that efforts are on track and allowing for adjustments as needed. Public engagement and education about the importance of regulating Venus's atmosphere can build support for these efforts. Informing people about the scientific and potential human benefits can generate the necessary backing for long-term investment. Research into alternative methods and technologies for atmospheric regulation continues to be important. Exploring new ideas and refining existing techniques can lead to more effective and efficient solutions. Testing atmospheric regulation methods in controlled environments on Earth or in space can provide valuable insights. These tests help address potential issues and optimize processes before full-scale implementation on Venus. Integrating atmospheric regulation with other terraforming efforts, such as creating a magnetic field and establishing floating habitats, is crucial for a cohesive strategy. Ensuring these efforts complement each other will enhance the overall success of making Venus habitable. As we advance in regulating Venus's atmosphere, we take significant steps toward transforming the planet into a more livable environment. These efforts reflect our commitment to exploring and adapting to new worlds, paving the way for future human settlements in the solar system. Generating and managing water on Venus is essential for supporting human life and establishing sustainable habitats. Water is a critical resource for drinking, agriculture, and industrial processes. One method to generate water on Venus is through atmospheric extraction. Venus's atmosphere contains trace amounts of water vapor, which can be captured and condensed into liquid water using advanced atmospheric processes. Electrolysis of carbon dioxide can also produce water. By splitting CO2 into carbon monoxide and oxygen, hydrogen can be introduced to form water. This process requires significant energy, but is a viable option for water generation. Transporting water from Earth is another approach, especially in the initial stages of colonization. Water can be delivered in tanks or produced on-site through chemical reactions involving hydrogen brought from Earth. Using chemical reactions to extract water from the sulfuric acid clouds is another innovative method. Sulfuric acid can be broken down into sulfur dioxide and water, providing a substantial source of water for human use. Recycling and purifying wastewater are crucial for maintaining a sustainable water supply. Advanced filtration and purification systems can ensure that water used in habitats, agriculture, and industry is continually recycled and reused. Storing water efficiently is essential for managing supply and demand. Large insulated tanks and reservoirs can be built to hold water, protecting it from evaporation and contamination, while ensuring a steady supply. Developing efficient irrigation systems for agriculture is vital for water management. Techniques such as drip irrigation and hydroponics minimize water usage while maximizing crop yields, ensuring food security. Monitoring water quality is critical for health and safety. Regular testing for contaminants and maintaining high purification standards help ensure that the water supply remains safe for all uses. Research into advanced water generation and management technologies continues to evolve. Innovations in desalination, condensation, and recycling are essential for improving water sustainability on Venus. International collaboration can enhance water generation and management efforts. Sharing technologies, research, and resources can lead to more effective solutions and ensure a reliable water supply for all missions. Public engagement and support for water generation initiatives are crucial. Educating people about the importance of water management and the innovative methods being developed can build the necessary backing for ongoing research and investment. Implementing pilot projects on Earth or in space can provide valuable data and refine techniques before deploying them on Venus. Successful tests can build confidence in the feasibility of these water generation methods. As we advance in generating and managing water on Venus, we move closer to creating a self-sustaining environment. Water is fundamental to life, and ensuring a reliable supply is a key step in establishing a permanent human presence on the planet. Integrating water generation with other terraforming efforts, such as regulating the atmosphere and creating a magnetic field, will enhance the overall success of making Venus habitable. These coordinated efforts reflect our commitment to overcoming the challenges of planetary colonization. The successful generation and management of water on Venus represent a significant milestone in our journey to expand human presence beyond Earth. These efforts showcase human ingenuity and determination, paving the way for future exploration and settlement in the solar system. Achieving long-term ecological stability on Venus is essential for supporting human life and creating sustainable habitats. Establishing self-sustaining ecosystems that can thrive in Venus's unique environment is a complex but vital goal. One key aspect of ecological stability is the introduction of diverse plant species. Plants play a crucial role in producing oxygen, absorbing carbon dioxide, and creating a balanced atmosphere. Selecting hardy, resilient species that can thrive in controlled environments is critical. Soil health and fertility are also essential. Developing soil with the right mix of nutrients, organic matter, and microorganisms can support robust plant growth. Techniques like composting and biochar application can enhance soil quality over time. Water management is crucial for maintaining ecological stability. Efficient recycling systems, water-saving irrigation techniques, and careful monitoring of water sources help ensure a reliable supply for both human use and agriculture. Energy sustainability is another critical factor. Renewable energy sources like solar and wind power must be harnessed and optimized to provide continuous power for habitats, greenhouses, and other infrastructure. Waste management systems are essential for ecological stability. Recycling and reusing materials, composting organic waste, and safely disposing of non-recyclable waste help maintain a clean and healthy environment. Climate control within habitats and greenhouses involves regulating temperature, humidity, and atmospheric composition. Advanced climate control systems can create ideal conditions for plant growth, mimicking Earth's environments as closely as possible. Pollution control measures must be in place to prevent contamination of air, water, and soil. Minimizing the release of harmful substances and using clean technologies contribute to a healthier ecosystem. Regular environmental monitoring is crucial. Tracking changes in soil health, water quality, air composition, and biodiversity helps identify potential issues early and allows for timely interventions to maintain stability. Integrating local resources into ecological systems enhances sustainability. Utilizing Venusian materials for construction and soil development reduces the need for imports from Earth and helps create a self-sufficient settlement. Developing closed-loop systems where waste products are repurposed into useful resources supports long-term ecological health. For example, converting organic waste into compost or biofuel ensures efficient use of available materials. Research into the interactions between different species and environmental conditions on Venus is essential. Understanding these dynamics helps optimize ecosystem design and management, promoting long-term stability. International collaboration in ecological research and resource management can enhance the effectiveness of these efforts. Sharing knowledge, technologies, and best practices ensures a more robust and resilient ecological system. Public engagement and education about the importance of ecological stability can build support for sustainable practices. Involving settlers in environmental stewardship fosters a culture of sustainability and responsibility. As we work towards long-term ecological stability on Venus, we lay the foundation for enduring human presence and expansion into the cosmos. These efforts ensure that future generations can thrive in a balanced and self-sustaining environment, embodying our commitment to sustainable exploration and settlement. Spacecraft and robotics are essential for exploring and terraforming Venus. They provide the tools and capabilities needed to study the planet, deploy infrastructure, and support human missions. Robotic missions are the first step in any planetary exploration. They gather crucial data about Venus's atmosphere, surface conditions, and potential resources. This information guides future missions and helps develop effective terraforming strategies. Landing a spacecraft on Venus is a significant challenge due to its extreme temperatures and high pressure. Advanced materials and engineering solutions are required to design landers and rovers that can operate in such harsh conditions. Orbiters play a critical role in studying Venus from above. They can map the surface, monitor atmospheric changes, and relay data back to Earth. These orbiters provide a continuous stream of information essential for planning and executing missions. Robotic landers equipped with drills and sampling instruments can analyze Venus's surface and subsurface. These missions can identify key resources and assess the feasibility of extracting materials needed for terraforming and habitation. Rovers designed to traverse Venus's rugged terrain will be crucial for exploration. These rovers need to be highly durable, autonomous, and capable of navigating the planet's diverse landscapes. They can conduct scientific experiments and lay the groundwork for human missions. Aerial drones can explore Venus's upper atmosphere, where conditions are more Earth-like. These drones can gather data, test technologies for floating habitats, and even deploy small sensors across different regions of the planet. Developing robotic systems for construction is vital for establishing infrastructure on Venus. Robots can build habitats, deploy solar panels, and set up life support systems, reducing the need for human presence in the initial stages. Robotic assistance in mining and resource extraction will be essential. Robots can operate in hazardous environments, extracting minerals and other materials needed for building and maintaining settlements. Spacecraft designed for transporting materials and supplies between Earth and Venus are critical. These vessels must be capable of carrying heavy loads and surviving multiple trips through the harsh conditions of space and Venus's atmosphere. Autonomous repair and maintenance robots will help ensure the longevity of infrastructure on Venus. These robots can perform routine inspections, repairs, and upgrades, minimizing the need for human intervention. Robotic research stations can be deployed to continuously monitor environmental conditions on Venus. These stations provide real-time data on temperature, pressure, atmospheric composition, and other key factors, helping to track progress and make adjustments as needed. Human missions to Venus will rely heavily on robotic support. Robots can prepare habitats, set up life support systems, and ensure that the environment is safe and ready for human arrival. They can also assist with daily tasks, making life easier for settlers. International collaboration in robotic technology and spacecraft development can enhance mission success. Sharing expertise and resources allows for more sophisticated and robust solutions, accelerating progress and reducing costs. As we advance our capabilities in spacecraft and robotics, we move closer to making Venus a habitable world. These technologies are the backbone of our exploration efforts, enabling us to push the boundaries of what is possible and paving the way for human settlement in the solar system. Advanced materials are crucial for the success of terraforming Venus. These materials must withstand extreme conditions, including high temperatures, high pressures, and corrosive environments. Developing heat-resistant materials is essential. Venus's surface temperatures reach up to 900 degrees Fahrenheit, so materials must maintain their integrity under intense heat. Corrosion resistance is another critical factor. The thick atmosphere contains sulfuric acid clouds, which can corrode standard materials. Advanced composites and coatings are needed to protect structures and equipment. Lightweight but strong materials are ideal for constructing floating habitats. These materials provide the necessary strength while minimizing weight, ensuring habitats remain buoyant in Venus's upper atmosphere. High-strength alloys can be used for structural components that require durability and stability. These alloys must perform well under Venus's unique environmental stresses. Radiation shielding materials protect inhabitants and electronic equipment from cosmic rays and solar radiation. Effective shielding is vital for long-term missions and human safety. Thermal insulation materials help regulate temperature within habitats. These materials maintain a stable internal environment despite the extreme external temperatures. Flexible materials are needed for building and maintaining infrastructure. These materials can adapt to shifting conditions and stresses, ensuring long-term durability and functionality. Self-healing materials can repair minor damages automatically. These materials enhance the longevity of structures and reduce maintenance needs, crucial for remote or autonomous operations. Transparent materials with UV protection are necessary for windows and observation ports. They allow light to enter while blocking harmful ultraviolet radiation. Nanomaterials offer unique properties that can be tailored for specific applications. They can improve strength, conductivity, and resistance to environmental stresses. Smart materials that respond to environmental changes can optimize performance. These materials can adapt to temperature fluctuations, pressure changes, and other variables. Recyclable materials support sustainable construction practices. Using materials that can be repurposed or recycled reduces waste and supports a closed-loop system on Venus. 3D printing materials enable on-site construction of habitats and equipment. Advanced printing techniques can use locally sourced materials, reducing the need for supplies from Earth. Biocompatible materials are important for agricultural and medical applications. These materials ensure that food production and healthcare systems operate safely and effectively. Collaborative research and development in advanced materials are essential for overcoming the challenges of Venus. International cooperation can accelerate innovation and lead to more robust solutions for future missions. Life support systems are essential for sustaining human life on Venus. These systems must provide air, water, food, and waste management to ensure the well-being of inhabitants. Air purification is critical. Life support systems must remove carbon dioxide and other harmful gases from the atmosphere, providing a steady supply of breathable oxygen. Water recycling is a key component. Advanced filtration and purification systems ensure that water used for drinking, cooking, and hygiene is continuously recycled and safe for consumption. Food production systems must be integrated into life support. Hydroponic and aeroponic systems can grow crops without soil, providing fresh food and contributing to oxygen production. Temperature regulation is vital for maintaining a stable environment within habitats. Life support systems must manage heating and cooling to ensure comfortable living conditions despite Venus's extreme external temperatures. Humidity control prevents mold and maintains air quality. Life support systems must regulate moisture levels to create a healthy living environment. Nutrient recycling supports agricultural systems. Waste products from plants and humans can be processed into fertilizers, ensuring a continuous supply of nutrients for crop growth. Waste management systems handle human waste and other refuse. These systems must safely process and dispose of waste, preventing contamination and supporting a closed-loop ecosystem. Energy supply is crucial for all life support functions. Solar panels and other renewable energy sources must provide a reliable power supply for all systems. Monitoring and control systems track environmental conditions. Sensors and automated systems ensure that life support functions are operating correctly and make adjustments as needed. Redundancy and backup systems enhance reliability. Multiple layers of life support systems ensure that if one system fails, others can take over, ensuring continuous support for inhabitants. Health and medical systems are part of life support. Facilities for medical care, emergency response, and routine health maintenance are essential for the well-being of the crew. Psychological support is also important. Life support systems should include facilities and programs to support mental health, addressing the challenges of living in an isolated and extreme environment. International collaboration in developing life support systems can lead to more robust solutions. Sharing expertise and technologies ensures that the systems are as effective and reliable as possible. As we advance in creating life support systems for Venus, we move closer to establishing sustainable human habitats. These systems are the backbone of any long-term mission, ensuring that humans can live and thrive in one of the most challenging environments in our solar system. Renewable energy sources are vital for sustaining human habitats on Venus. They provide the necessary power for all systems, reducing reliance on imported fuels and supporting long-term sustainability. Solar power is the most abundant renewable energy source on Venus. The planet receives a significant amount of sunlight, making solar panels an efficient way to generate electricity for habitats and other infrastructure. Advanced solar panel technology is crucial. Panels must be highly efficient and resistant to Venus's harsh conditions, including extreme heat and corrosive atmosphere. Energy storage is essential for managing solar power. Batteries and other storage systems ensure a steady supply of electricity, even during periods when sunlight is not available. Wind energy can also be harnessed on Venus. Although the surface winds are slow, the upper atmosphere experiences high-speed winds that can drive turbines and generate power. Geothermal energy is another potential source. Venus's volcanic activity and internal heat can be tapped into using geothermal power plants, providing a constant and reliable energy supply. Hydroelectric power is less viable due to the lack of liquid water on Venus, but innovative methods to generate electricity from other fluid movements, such as atmospheric flows, could be explored. Thermoelectric generators can convert heat directly into electricity. These devices can harness the intense heat from Venus's surface or volcanic activity to produce power. Piezoelectric materials generate electricity from mechanical stress. These materials could be used in structures that flex or vibrate in Venus's atmospheric conditions, producing small amounts of power. Bioenergy can be produced from organic waste. Bioreactors convert waste into biogas, which can be used to generate electricity or heat, supporting a closed-loop ecosystem. Hydrogen fuel cells offer another renewable energy source. Hydrogen can be produced through electrolysis of water and then used in fuel cells to generate electricity, providing a clean and efficient power supply. Combining multiple renewable energy sources enhances reliability. A diversified energy portfolio ensures that if one source is unavailable, others can compensate, providing a stable energy supply. Energy efficiency is as important as generation. Advanced insulation, energy-saving technologies, and efficient system designs reduce overall power consumption, making renewable energy sources more effective. International collaboration in renewable energy technology can accelerate progress. Sharing innovations and best practices ensures the development of robust and efficient energy systems for Venus. Public support and investment in renewable energy research are crucial. Educating people about the benefits and challenges of renewable energy on Venus can build the necessary backing for ongoing development and deployment. As we advance in harnessing renewable energy sources for Venus, we pave the way for sustainable and self-sufficient human habitats. These efforts reflect our commitment to clean energy and resilience, ensuring that future generations can thrive in a new and challenging environment. Artificial intelligence plays a critical role in terraforming efforts on Venus. AI systems provide advanced capabilities for managing complex tasks and optimizing processes, essential for successful missions. One key application of AI is in data analysis. AI can process vast amounts of data from sensors and instruments, identifying patterns and trends that human analysts might miss. This capability is crucial for monitoring environmental changes and making informed decisions. AI-driven robotics enhance exploration and construction on Venus. Autonomous robots equipped with AI can navigate the harsh terrain, perform maintenance, and build infrastructure with minimal human intervention. Machine learning algorithms can optimize resource allocation. By analyzing data on energy usage, water consumption, and material needs, AI systems can ensure that resources are used efficiently and sustainably. AI can improve life support systems by continuously monitoring and adjusting conditions. These systems can respond to changes in temperature, humidity, and air quality, ensuring a stable and safe environment for inhabitants. Predictive maintenance is another valuable AI application. AI can predict when equipment and systems are likely to fail, allowing for proactive maintenance and reducing downtime. AI enhances communication and coordination between different teams and systems. Intelligent communication networks ensure that information flows seamlessly, supporting collaboration and quick decision-making. In agriculture, AI can optimize crop growth by monitoring soil conditions, adjusting nutrient delivery, and predicting harvest times. These capabilities are essential for maintaining a reliable food supply on Venus. AI-driven climate modeling can predict the effects of various terraforming efforts. By simulating different scenarios, AI helps scientists understand the potential impacts and refine their strategies for optimal results. Energy management systems benefit from AI by balancing supply and demand. AI can integrate multiple renewable energy sources, manage storage systems, and ensure a consistent power supply. AI can also play a role in environmental protection. Intelligent monitoring systems can detect and mitigate pollution, ensuring that terraforming efforts do not harm the Venusian environment. Educational programs can be enhanced with AI, providing personalized learning experiences for inhabitants. AI tutors and training programs ensure that settlers are well prepared for life on Venus. Security systems benefit from AI through advanced surveillance and threat detection. AI can monitor for potential hazards, unauthorized access, and other security concerns, ensuring the safety of inhabitants. AI can facilitate scientific research by automating data collection and analysis. This capability allows scientists to focus on interpretation and discovery, accelerating the pace of research and innovation. As we integrate AI into terraforming efforts, we unlock new possibilities for making Venus habitable. These intelligent systems provide the tools and insights needed to overcome challenges and achieve sustainable human presence on the planet. Expanding human habitats on Venus involves gradually increasing the number and size of living spaces to accommodate more inhabitants. This process requires careful planning and the use of advanced technologies. Initial habitats will be relatively small, designed for short-term missions. These early structures will provide critical data on how to build larger, more permanent settlements. As we learn from these initial habitats, we can begin constructing larger, more complex living spaces. These expanded habitats will support long-term habitation and provide more room for residents. Building vertically is an effective way to expand habitats without taking up additional surface area. Multi-level structures can house more people and facilities within a smaller footprint. Modular construction techniques allow for flexible and scalable habitat design. Modules can be added or reconfigured as needed, accommodating growing populations and changing needs. Underground habitats offer additional living space while providing natural protection from radiation and extreme temperatures. These structures can be integrated with surface habitats to create a cohesive living environment. Developing sustainable energy solutions is crucial for expanding habitats. Renewable energy sources, such as solar and wind power, must be scaled up to meet the increased demand from larger settlements. Water management systems must also be expanded. Advanced recycling and purification systems will ensure a steady supply of clean water for a growing population. Agricultural facilities need to be scaled up to provide food for more inhabitants. Hydroponic and aeroponic systems can be expanded, and new methods of food production can be explored. Transport infrastructure must evolve to support larger populations. Efficient transportation systems, including rovers and aerial vehicles, will facilitate movement within and between habitats. Communication networks must be robust and scalable. Reliable communication is essential for coordinating activities, sharing information, and maintaining connections with Earth. Healthcare facilities must grow to meet the needs of an expanding population. Medical centers equipped with advanced technologies will ensure that inhabitants receive comprehensive care. Educational facilities are also crucial. Schools and training centers will provide education and skills development for all age groups, supporting a knowledgeable and capable community. Recreational and cultural facilities enhance the quality of life. Parks, theaters, and other amenities will create a vibrant and enjoyable living environment, promoting mental and physical well-being. Safety and security measures must be continually improved. Expanding habitats require enhanced systems to protect inhabitants from potential hazards and emergencies. International collaboration will be key to the successful expansion of human habitats. Sharing expertise, resources, and technology will accelerate progress and ensure that Venus becomes a thriving, multinational settlement. As we expand human habitats on Venus, we pave the way for a sustainable and resilient future. These efforts demonstrate our commitment to exploring and inhabiting new worlds, creating a legacy of innovation and exploration for generations to come. Scientific discoveries on Venus can transform our understanding of planetary science and the conditions necessary for life. These discoveries are integral to making the planet habitable. Exploring Venus's geological history can reveal insights into its volcanic activity and tectonic movements. Understanding these processes can help us predict future geological events and their impact on potential habitats. Studying Venus's atmosphere provides crucial data on its composition and dynamics. This information is essential for developing effective methods to alter and regulate the atmosphere for human habitation. The discovery of active volcanoes on Venus could indicate that the planet is still geologically active. This activity could play a role in future terraforming efforts, providing heat and potentially usable materials. Now, investigating the presence of lightning and electrical storms in Venus's atmosphere can enhance our understanding of atmospheric electricity and its effects on climate and weather patterns. Finding evidence of water, even in small amounts, could be a game changer. Water is essential for life, and understanding its distribution on Venus can guide efforts to create sustainable water sources. Discovering extremophiles, or life forms that thrive in extreme conditions, could revolutionize our approach to terraforming. These organisms might be adapted for use in transforming the Venusian environment. Mapping Venus's surface in detail can uncover hidden features such as caves, cliffs, and valleys. These natural formations could be used to our advantage in building shelters and other infrastructure. Understanding the chemical composition of Venusian rocks and soil is crucial for developing construction materials. Local resources can be utilized to build habitats and other structures, reducing the need for imported materials. Studying the greenhouse effect on Venus can provide valuable insights into climate change. This knowledge can inform both our efforts on Venus and our understanding of similar processes on Earth. Investigating the potential for photosynthesis under Venusian conditions can guide the development of plants that can thrive in the planet's environment. These plants would be crucial for oxygen production and food supply. Understanding the interactions between solar wind and Venus's atmosphere can help in designing protective measures against radiation. This knowledge is essential for creating safe living conditions. Researching Venus's magnetic field, or lack thereof, can provide clues about the planet's core and its geological history. This information is important for understanding the planet's overall structure and stability. Discovering the presence and effects of sulfuric acid in the atmosphere can lead to new methods for mitigating its impact. This knowledge is vital for protecting habitats and machinery from corrosion. Studying the distribution and movement of clouds on Venus can improve climate models. Accurate models are essential for predicting weather patterns and planning terraforming activities. Uncovering the history of Venus's climate can reveal why it diverged so dramatically from Earth's. Understanding these differences can guide our efforts to create a more Earth-like environment on Venus. These scientific discoveries not only advance our knowledge of Venus, but also have broader implications for planetary science and astrobiology. They lay the groundwork for future exploration and the eventual transformation of Venus into a habitable world. Economic opportunities on Venus are vast and varied, offering potential for significant financial and technological advancements. Developing a sustainable economy on Venus involves leveraging local resources and innovative technologies. Mining Venus's surface for valuable minerals can provide a significant economic boost. The planet's geological activity may have concentrated precious metals and other valuable resources, which can be extracted and utilized. The development of advanced materials required for Venus's harsh environment can lead to new industries. These materials can be marketed for use on Earth and other space missions, creating a new market segment. Renewable energy technologies developed for Venus can have applications on Earth. The innovations in solar, wind, and geothermal energy can be adapted to improve energy efficiency and sustainability on our home planet. Tourism could become a lucrative industry. As technology advances, creating safe and comfortable travel experiences to Venus can attract tourists eager to explore the unique landscapes and phenomena of another planet. Scientific research and development on Venus can drive economic growth. Funding for research projects and the commercialization of discoveries can lead to the creation of new industries and job opportunities. The construction of habitats and infrastructure on Venus requires a skilled workforce. This need can create jobs in engineering, construction, and technology sectors, both on Earth and on Venus. Establishing agricultural systems on Venus can lead to advancements in food production technology. These innovations can improve agricultural practices on Earth, leading to more efficient and sustainable food production. Transportation technologies developed for travel to and from Venus can revolutionize space travel. These advancements can reduce the cost of space missions and open new opportunities for exploration and commercial ventures. Developing a Venusian economy can attract investments from private companies and international organizations. This influx of capital can drive innovation and accelerate the pace of development. Education and training programs tailored to the needs of Venus's economy can prepare the next generation of scientists, engineers, and entrepreneurs. These programs can create a skilled workforce ready to tackle the challenges of living and working on Venus. Collaborative international projects on Venus can enhance diplomatic relations and economic ties between countries. Working together on large-scale projects can foster cooperation and mutual benefits. The technology and infrastructure developed for Venus can be applied to other planetary bodies, expanding economic opportunities beyond Venus. These technologies can support missions to Mars, the Moon, and other destinations. Intellectual property generated from Venusian innovations can be patented and commercialized, creating revenue streams for individuals and organizations involved in these developments. Venus can become a hub for space-based manufacturing. The unique conditions on Venus can support processes that are not feasible on Earth, leading to the production of high-value goods and materials. As we develop economic opportunities on Venus, we pave the way for a self-sustaining economy that supports long-term human habitation. These efforts contribute to the overall goal of expanding human presence in the solar system and unlocking the vast potential of space. Advancements in technology are crucial for the successful exploration and terraforming of Venus. These technological innovations will enable us to overcome the planet's extreme conditions and create a habitable environment. Developing new materials that can withstand Venus's high temperatures and corrosive atmosphere is a priority. These materials will be used in constructing habitats, vehicles, and other essential infrastructure. Improving energy generation and storage technologies is vital. Advanced solar panels, wind turbines, and geothermal systems will provide reliable power for all operations on Venus. Robotics and automation will play a significant role. Autonomous robots can perform tasks such as construction, maintenance, and mining, reducing the need for human presence in hazardous areas. Artificial intelligence will enhance decision-making and operational efficiency. AI can process data, predict outcomes, and optimize resource management, ensuring the success of various projects on Venus. Advanced life support systems are essential. These systems must provide air, water, food, and waste management while maintaining a stable environment for inhabitants. Innovations in transportation technology will make travel to and from Venus more efficient. Developing faster and more reliable spacecraft will facilitate regular missions and supply runs. Water generation and recycling technologies will ensure a continuous supply of clean water. These systems must extract water from the atmosphere, purify it, and recycle it for reuse. Agricultural advancements will support sustainable food production. Hydroponics, aeroponics, and genetically modified crops will enable efficient and resilient farming practices. Developing communication technologies is crucial for maintaining contact with Earth. Reliable communication networks will support data transmission, collaboration, and personal communication. Medical technology must advance to address the unique health challenges of living on Venus. Innovations in remote medical care, emergency response, and health monitoring will ensure the well-being of inhabitants. Building smart infrastructure will enhance living conditions. Intelligent systems can manage energy, water, and climate control, adapting to changing conditions and optimizing resource use. Virtual and augmented reality can improve training and operations. These technologies can simulate Venus's environment, allowing for better preparation and real-time support for various tasks. Developing new propulsion systems will make space travel more efficient. Advanced engines and fuel technologies can reduce travel time and costs, making Venus more accessible. Continuous research and development in these areas will drive technological progress. Collaborative efforts between governments, private companies, and research institutions will accelerate innovation. As we achieve these technological advancements, we move closer to making Venus a viable home for humanity. These innovations not only support our goals on Venus, but also have the potential to transform life on Earth and beyond. Securing the future of humanity involves expanding our presence beyond Earth. Establishing a foothold on Venus is a significant step in this direction, ensuring our survival in the face of potential global catastrophes. Diversifying our planetary habitats reduces the risk of extinction from events like asteroid impacts, nuclear war, or pandemics. By having a thriving population on Venus, we create a backup for humanity. Advancing space colonization technology also prepares us for future exploration. The skills and knowledge gained from living on Venus can be applied to missions to other planets and moons in our solar system. Creating sustainable habitats on Venus challenges us to innovate. These innovations can lead to breakthroughs in energy, materials science, and life support systems, benefiting both space and Earth-based applications. Building a society on Venus offers new opportunities for social, political, and economic experimentation. It allows us to test and implement new governance models and societal structures in a unique environment. Venus can serve as a base for scientific research. The planet's unique conditions provide a natural laboratory for studying extreme environments, climate science, and planetary geology. The development of Venus as a habitable planet can inspire future generations. It fosters a sense of exploration and adventure, encouraging young people to pursue careers in science, technology, engineering, and mathematics. International collaboration on Venus missions can strengthen global cooperation. Working together on a shared goal can improve diplomatic relations and foster a spirit of unity and teamwork among nations. Securing resources from Venus and other planets can reduce the strain on Earth's resources. Mining and utilizing extraterrestrial materials can support our planet's sustainability efforts. Exploring Venus helps us better understand our place in the universe. It can provide insights into the formation and evolution of planets, enhancing our knowledge of planetary systems. The challenges of living on Venus push us to overcome technological and logistical obstacles. These efforts build resilience and adaptability, qualities essential for our long-term survival and success. A successful colony on Venus sets a precedent for future space colonization. It proves that humanity can thrive in environments vastly different from Earth, opening the door to even more ambitious endeavors. The pursuit of terraforming Venus drives innovation in multiple fields. From energy production to environmental engineering, the technologies developed for Venus can have widespread applications. Ensuring a future on Venus involves ethical considerations. We must approach terraforming and colonization with respect for potential ecosystems and with a commitment to preserving the planet's natural state as much as possible. Ultimately, securing the future of humanity through the colonization of Venus embodies our innate drive to explore, innovate, and survive. It represents our willingness to adapt and thrive in new environments, ensuring the continuity and prosperity of human civilization for generations to come. In summary, terraforming Venus presents both immense challenges and incredible opportunities for humanity. By understanding the planet's physical characteristics and atmospheric composition, we lay the groundwork for effective strategies. Addressing the challenges of high temperatures and pressure is crucial. Cooling the planet and reducing atmospheric pressure are primary steps toward creating a more habitable environment. Introducing microorganisms can help alter the atmosphere and improve soil conditions, making it possible to grow food and sustain life. Floating habitats offer an immediate solution to living on Venus, while surface conditions are being transformed. Creating a magnetic field is essential for protecting the atmosphere and future inhabitants from solar and cosmic radiation. This involves advanced technological solutions and international collaboration. Regulating the atmosphere to reduce carbon dioxide levels and sulfuric acid clouds is a critical step. This process will make Venus's environment more stable and conducive to life. Water generation and management are vital for survival. Extracting water from the atmosphere and recycling it efficiently will ensure a reliable supply for human use. Long-term ecological stability is key to sustaining human life. Developing diverse ecosystems and integrating local resources will support a balanced and self-sustaining environment. Spacecraft and robotics are indispensable tools for exploration and construction. They enable us to gather data, build infrastructure, and perform essential tasks in Venus's harsh environment. Advanced materials are necessary for constructing habitats and equipment that can withstand Venus's extreme conditions. Innovations in materials science will drive progress in this area. Life support systems must provide air, water, food, and waste management while maintaining a stable environment. These systems are the backbone of any long-term mission. Renewable energy sources will power all aspects of Venusian habitats. Harnessing solar, wind, and geothermal energy is crucial for sustainability. Artificial intelligence enhances all aspects of terraforming efforts. AI-driven systems improve efficiency, decision-making, and resource management. Expanding human habitats involves scaling up infrastructure and integrating advanced technologies. Modular and flexible designs will accommodate growing populations. Scientific discoveries on Venus will advance our knowledge of planetary science and the conditions necessary for life. These findings will guide future exploration and terraforming efforts. Economic opportunities arise from developing Venus's resources and technological innovations. These advancements will benefit both space and Earth-based economies. Securing the future of humanity involves expanding our presence beyond Earth. Establishing a foothold on Venus is a significant step in ensuring our survival and prosperity. Current progress in the terraforming of Venus involves several key initiatives and ongoing research. Scientists and engineers are working on developing the technologies needed to make Venus habitable. Robotic missions have been sent to Venus to gather data about its atmosphere, surface, and geological activity. These missions provide critical information that guides our terraforming strategies. Laboratories on Earth are simulating Venusian conditions to test materials and technologies. These simulations help us understand how our equipment and infrastructure will perform on Venus. Advances in solar power technology are being made to harness Venus's abundant sunlight. New solar panel designs are more efficient and can withstand the harsh environment of Venus's upper atmosphere. International collaborations are forming to tackle the challenges of terraforming Venus. Countries and space agencies are pooling resources and expertise to accelerate progress and share findings. Research into genetically engineered microorganisms is progressing. Scientists are developing bacteria and algae that can survive Venus's conditions and help transform its atmosphere. Efforts to design floating habitats are underway. Engineers are creating prototypes and conducting experiments to ensure these habitats can sustain human life in the upper atmosphere of Venus. Projects to create artificial magnetic fields are in the conceptual and experimental stages. Researchers are exploring different methods to generate a protective magnetic shield around Venus. Atmospheric regulation techniques are being developed. Experiments with chemical reactions to reduce carbon dioxide levels and sulfuric acid concentrations are showing promising results. Water extraction technology is advancing. New methods for capturing and purifying water from Venus's atmosphere are being tested, ensuring a sustainable water supply for future inhabitants. Life support systems are being refined. Innovations in air purification, water recycling, and waste management are critical for maintaining stable living conditions in Venusian habitats. Artificial intelligence is being integrated into various aspects of the mission. AI systems are being designed to manage resources, monitor environmental conditions, and assist with decision-making. Timelines for these projects vary. Initial robotic missions and data collection have already been completed, while some technologies, like floating habitats and magnetic field generators, are expected to take several decades to develop and deploy. Pilot projects and test missions are planned for the coming years. These smaller-scale initiatives will validate our technologies and provide practical insights before full-scale terraforming efforts begin. Overall, the timeline for making Venus habitable is long-term. It involves continuous research, development, and iterative testing, with the goal of establishing a sustainable human presence on Venus within the next century. Upcoming missions and projects are set to advance our efforts in terraforming Venus. These initiatives will build on current research and bring us closer to establishing a human presence on the planet. One major project is the launch of advanced robotic explorers. These robots will map the surface of Venus in greater detail, identifying potential sites for future habitats and resource extraction. A series of atmospheric probes will be deployed to study the upper layers of Venus's atmosphere. These probes will gather data on wind patterns, chemical composition, and temperature variations. Plans are underway to send a fleet of solar-powered drones to Venus. These drones will operate in the upper atmosphere, conducting experiments and relaying data back to Earth. Collaborative international missions are being organized to pool resources and expertise. Joint efforts will accelerate the development of key technologies and ensure a coordinated approach to terraforming. The construction of a prototype floating habitat is scheduled for the next decade. This habitat will be tested in the upper atmosphere of Venus to evaluate its performance and sustainability. Experiments with genetically engineered microorganisms will be conducted in space-based labs. These experiments aim to develop strains that can thrive on Venus and assist in atmospheric transformation. A mission to deploy a magnetic field generator in orbit around Venus is in the planning stages. This project will test the feasibility of creating an artificial magnetosphere to protect the planet's atmosphere. Research stations will be established on Venus to continuously monitor environmental conditions. These stations will provide real-time data to support ongoing terraforming efforts and ensure the safety of future human missions. A large-scale project to reduce carbon dioxide levels in Venus's atmosphere will be initiated. This project will utilize chemical reactions to sequester CO2 and lower atmospheric pressure. Innovative water extraction systems will be tested on Venus. These systems will capture and purify water vapor from the atmosphere, providing a sustainable water source for future settlers. The development of advanced solar power stations is a priority. These stations will harness the abundant sunlight on Venus, providing reliable energy for all operations and habitats. AI-driven systems will be deployed to manage resources and optimize terraforming processes. These intelligent systems will monitor conditions, predict outcomes, and make adjustments in real time. An international consortium will fund and oversee these upcoming missions and projects. Collaboration among nations will ensure a shared vision and pooled resources for the terraforming of Venus. Public engagement and education campaigns will accompany these missions. Informing and inspiring the global community will build support for the long-term goals of space exploration and habitation. As these upcoming missions and projects progress, they will bring us closer to realizing the dream of making Venus a new home for humanity. Each step forward represents a significant milestone in our journey to expand beyond Earth and secure our future among the stars. In this video, we've embarked on an extraordinary journey to explore the possibility of terraforming Venus and Mars. We started by defining what terraforming entails and why it holds immense importance for the future of humanity. By expanding our horizons to other planets, we not only ensure the survival of our species, but also open up new avenues for scientific discovery and economic opportunities. We then delved into the detailed characteristics of Venus and Mars, examining their physical conditions, atmospheric compositions, climates, and potential resources. Understanding these fundamental aspects is crucial, as it informs the strategies we need to employ to make these planets habitable. Next, we discussed the formidable challenges of terraforming these planets, from reducing atmospheric pressure on Venus to generating a magnetic field on Mars. Despite these challenges, the potential benefits make the endeavor worthwhile, promising new frontiers for human habitation and resource utilization. Our exploration covered innovative concepts like introducing microorganisms to alter the atmospheres, creating floating habitats on Venus, and constructing underground colonies on Mars. Each of these ideas represents a stepping stone towards transforming these inhospitable worlds into thriving environments. We highlighted the role of advanced technology in making terraforming possible. From AI-driven resource management to robotics for construction and maintenance, technological advancements are at the heart of our ability to adapt and thrive on other planets. Moreover, we touched on the current progress and upcoming missions that aim to gather more data and test new technologies. These initiatives, supported by international collaboration, are essential for making terraforming a reality. As we conclude, remember that these discussions are just the beginning. The future of humanity on other planets is a testament to our ingenuity and perseverance. If you enjoyed this video, please like and subscribe to our channel. Don't forget to check out the rest of our videos for more fascinating insights into space exploration and other scientific wonders. Your support helps us continue to bring you exciting content and share the latest advancements in our quest to explore the cosmos.